Well, hello everyone, and welcome back to Adrian's Digital Basement. The video you're about to watch is a supercut of the entire 5-part series on the Plexus P20. If you haven't already watched the series, or you want to kind of catch up and watch it again, well, here is your opportunity. This video is going to be rather long, so you can just set it on and let it play in the background and enjoy me figuring out this computer start to finish. It'll be the process of me opening this computer up for the very first time, taking a look inside, investigating what this machine's all about, and then trying to get it working. This supercut does not contain any new footage versus what was in the first 5 parts. There is lots of stuff that's happened with this machine since the making of the first 5 parts, and once I get over being sick, which I'm still fighting COVID right now, I'm gonna get right back into it and then start covering all the amazing, and I mean amazing, things that have happened around this machine since making of part 5. So in the meantime, enjoy this long supercut. This is the first one I've ever done. And well, yeah, without further ado, let's get right to it. On today's video, we're going to be taking a look at this rather large computer. This is a Plexus P20, which is a computer that, well, I don't really know much about it, and in fact, the only documentation that exists about this computer on the internet is simply these 2 pages. That is it. Since I was given this computer, I haven't attempted to turn it on. I haven't even opened it up or looked inside. So in this video, I think we're just going to be exploring what's inside of this machine. And if there's a hard drive, which I think there might be on the front here, looks like there is, then maybe I'll pull that out and we'll try to image it. And that's because there's really no software available for this thing either. And if we have any hopes of getting this thing to do anything, we're gonna need to recover the data off that hard drive. Before we take a tour of the outside of the machine and open it up and take a look inside, let's review that little pamphlet that I found that seems to be the only documentation about this computer, so we at least know what we're talking about when we look inside. So thank you, BitSavers, for having some documentation online so we at least know a little bit about this thing. It says here, Plexus P15/P20 Brochure 1985. And the model sticker on the back of this computer says Plexus P/20. So this computer appears to be a multi-processor architecture, high-performance 6810 multi-user Unix-based system with a SCSI disk interface up to 132 or 152 megabytes of storage, floppy drive, streaming tape. It does have a tape drive in it as well. There are 2 flavors of this computer, and as I mentioned, this is the P20, so the higher model. It's designed for the popular Unix operating system. The P15 supports 8 users, and the P20 adds the addition of an intelligent communication processor, the ICP, which extends the configurability to 16 users. It seems that both of these computers support 2 Motorola 6810 microprocessors, which of course are 32-bit processors. Both of these run Unix 5 Release 2. This is Plexus's implementation, and that's why if the hard drive is unrecoverable or unreadable, that's pretty much going to be the end of this video unless someone can dig up some additional software for this thing. Designed for office use, it's quiet. It's got this giant fan on the back. I guess compared to like mini computers and things like that at the time, maybe for a multi-user system this was relatively quiet, but it's such a huge computer. It'd have to be tucked away into like a closet somewhere, otherwise people will probably complain about the noise. So when it comes to the fact that this thing is a multi-processor system, it says that it links a powerful 1632-bit job processor with a second I/O processor of equal power to remove I/O processing overhead from the job processor. So it's not multi-processor as in 2 primary processes can run concurrently. It seems that one of the processors is actually handling all of the user tasks and the second 6810 is handling all the I/O. That's still kind of cool because it takes off all the I/O overhead from the main processor, so like disk activity and say tape I/O can really happen in the background without affecting performance of the main processor. Now in the photograph of these 2 computers, the one thing I'm a little worried about is I don't have the key for this system. It does have a keyhole on the front there, and I suppose worst case we'll have to just drill out the lock. If we open the computer and we find that it's just some pins that go to a little board, we can just jumper over them. Here's a little block diagram of the system, so DRAM and memory map. And then we have the two processors there, the job processor, which has its own bus, along with the IO processor with its own IO bus. It looks like from this diagram, they both share the same DRAM, which is kind of cool. That means that the IO processor can save stuff to disk out of the main DRAM while the job processor is accessing other parts. There must be something that arbitrates the access of the two CPUs to the DRAM though, and I'm assuming that's maybe this memory map here with these arrows. It looks like the 6810 has some static RAM as well on its own bus. Probably if it needs to copy some data out of the regular DRAM, puts it in static RAM, and then it can work on saving it to disk or accessing the tape drive, things like that. Now this is obviously that extra capability the P20 has. It has a multi-bus interface, and I think Intel came up with multi-bus. Was used on a bunch of different systems. It's kind of like the S100 bus in that it was somewhat adopted by other companies. Obviously there's nothing Intel based in this machine, being 6810s. And we have some kind of additional multi-bus backplane inside that case, I guess. So we'll have to see what kind of cards are installed in there, and looks like you can have additional stuff. This is the one that it comes with. It mentioned that on that first page, but then it has, well, other multi-bus controllers, which you can add. On the third page, talks about the fact that there are some self-diagnostics in here. Let's hope that they work and that they're easy to follow because, well, there's just no documentation, so we are on our own. The CPUs run at 12.5 megahertz, looks like 64K of ROM, and we have that 16K of static RAM for the IO processor. And it looks like we have up to 8 megabytes of address space available for DRAM. The 6810 is basically just like the 68000 with some slight optimizations. It can support up to 16 megabytes of RAM or RAM, ROM, and other types of devices on the bus. And it looks like they chose 8 megabytes. The Macintosh, of course, is famous for only supporting 4 megabytes of RAM, but then something like the Amiga does support 8 megabytes on the 68000 machine. So kind of similar in that way. There are 8 serial ports on the machine. We'll see that in a second when we look at the back. They're just 9 pins, except for I think a couple of them might be 25 pin. It's handy that we don't need some kind of breakout cable that I don't have, so that makes hooking up terminals very easy. Looks like the additional card in the P20 is some 16-bit processor that's on that multi-bus interface. We'll have to take a look at that. 32K of RAM there, 16K of ROM, and it looks like some additional serial interfaces are available there. The job processor, which is the one that the operating system, or at least like the user processes run on, is also running at 12.5 megahertz, has 8 megabytes of RAM. It does have a battery backed up clock calendar. That's pretty worrisome. I just saw that. I actually looked at this before, but I didn't notice that it has a clock. Hopefully that didn't leak and damage anything. And it says here that the memory capabilities of the system is only 2 megabytes. So even though it has 8 megs of address space available for RAM, 2 megabytes is all you get. Standard 256 kilobit DRAM though, and I saw up above it does use parity, so there'll be 9 chips of those. Luckily that's really easy. I have plenty of those chips, so if there's any RAM problems, we should hopefully be able to solve them. And on the final page, looks like the 5¼ inch floppy drive, which is in there, is a 96 track per inch drive, which is just typical like high density format. It's probably running a double density though. Oh yes, it is 640 kilobytes here. So on a PC, that would be 720 kilobytes for an 80 track disc, double sided. So pretty standard. So if the floppy drive doesn't work, that's no problem. I can put a spare in there pretty easily. And the tape drive is a QIC11, 45 megabytes per tape. That's a 9-track tape drive. I don't have any of those tapes. I think they pretty much self-destruct with the rubber and the belts and stuff inside. And what's worrisome is it's quite possible the original operating system for this machine was distributed on tape. And you would have a boot floppy of some kind, and then it would use a tape to restore the OS back onto a hard drive. Say if you had a hard drive crash, you had to start from scratch. That means it's probably unlikely that anyone ever archived those tapes. So that's probably why there's no software floating around for this thing. So let's hope that the hard drive in here is working so we can try to recover it and hopefully gain access to the Unix system that's on here. And down at the bottom, the very last thing, it says Plexus Computer Incorporated, 3833 North 1st Street from San Jose, California, and the date there, 1984, 1985, Plexus Computer Inc. Okay, over to the actual hardware. So on the top of the P20, we have a full height 5¼ inch floppy drive, although inside I've seen these before, it's just a half height mechanism. Looks like there's a blank here, maybe for the hard drive, a half height hard drive of some kind. And then there's the tape drive mechanism right there. It did say in the documentation that it was SCSI. Moving down, we have the Plexus logo embossed into the plastic. Pretty nice design element. And on the upper right corner of the front panel, we have the status display, P20, and we have 0 through 7, which is obviously for the active users, I guess. And it does say system power, and there's that key cylinder, which I don't have the key for. Looks like the glue is coming off a little bit here if it does move. We have LEDs in all the positions except for 3 and 2, which maybe those fell inside. We'll have to see when we get this apart. I had to move the camera pretty far back just to get in the sheer size of this thing. It is very heavy and very large, big swath of beige there. It's actually a metal computer as well, so moving this thing around is it's not easy. This large plastic piece at the bottom here, which contains the feet, also is an air intake of sorts because, well, there seems to be a big gap in there, and I'm assuming air enters the bottom here and then goes into the case. On the back of the machine, it's pretty large with this huge fan at the top. We have serial ports starting with 0. The board does seem to be moving around a little bit. 0 through 5, a little bit of rust on this screw right here, and then we have an access panel of some kind, which maybe that's for that expansion interface that uses those multi-bus cards. And then we have two 25-pin serial ports labeled 6 and 7. Looks like some kind of an expansion interface here, some pin header thing. Maybe this is for a UPS. It did mention that in the documentation that it supported an external UPS. Here's the mains AC input with a fuse and a voltage selector. It's multi-voltage, and there's the model number and serial number for the computer. I am definitely not just going to plug this in and try to turn it on. We're going to open this thing up and take a look inside because I want to get that hard drive out of here and hook that up externally to see if we can image it. So let's see how serviceable this thing is. I have a little screw holder here for loose screws if I take any out. And I'm just going to start here where it says open or close. I'm assuming we turn counterclockwise for loosening it. Okay, these seem to be captive. That turned and then stopped. And now it's just a matter of figuring out, oh, it's sliding forward. Okay, the entire top chassis seems to slide forward with the front panel. So let's turn this around so we can slide this off and reveal the insides. You know what, we're looking at the bottom of the board. Okay, that might be okay. Let's just get this off here. Ooh, it's so big. It is so big. Wow, wow, look at that. It's huge. It's such a big circuit board, and there's so many bodge wires on it. That is freaking amazing. So right there we have the clock battery, and luckily it's in one of those epoxy things, kind of like a Dallas clock. That's excellent. So that means it hasn't leaked anywhere on the board. If it had, it would have caused massive damage. Looks like the board is somewhat relatively easy to service. There are these little thumb screws right here that probably allow it to come out somewhat easily. Now I'm noticing right off the bat, there's something funny happening at the front of the case. This board here, which connects there, is like the expansion chassis, probably for the multi-bus stuff. It's just kind of loose. And that comes away. And I don't know if this got banged around like in shipping or something. Pulling that off, there's that expansion board. Now the funny thing is this doesn't look like multi-bus to me. I thought multi-bus has this, plus an extra little pin header, a higher density one, down on the side. Now what was this board here? This thing just simply has a bunch of resistors on it. That's kind of odd. Is this just to burn power? Now, if you look at the main motherboard here, you can see a row of pins. There's obviously some type of an expansion interface or header connected here with something plugged in on the back. And when I look down inside here, I can see that there's an additional board there. And obviously this is the large hard drive that's in here, so I'm gonna need to figure out how to get this out of here so we can try to image it. This, I'm assuming, is the power supply unit for the machine. And hopefully that comes across on the camera, but there, this board right there that's sandwiched on, connected with this connector right there, that's obviously the DRAM board. There's a whole bunch of DRAM there. The expansion backplane, part of the P20, has these levers here, which are kind of cool. Looks like you can twist these to release the tension on this and get the cards more easily in and out. I think it's a kind of a locking mechanism. When you twist them into this one position, it clamps down on the card to prevent them from coming out. And yes, indeed, it says here to open these, you turn them that way, and it opens them, and turning them left, I guess, latches down the card edge connector. So let's give that a test. I'm gonna switch this to the open position. Yeah, look at that. Wow, it opens that whole thing up, and I can place this card into the slot, turn this back to the closed position. Yeah, and I think that's grabbing onto it now. I have to say, I don't think I've ever seen that kind of mechanism before, but kind of cool. With the computer rotated around, we can see what looks like a giant power supply board here. I'm assuming both of these are power supplies. This is probably an additional power supply, now that I think about it, for the multi-bus interface. And this board here, which has a ton of wires there, must be the power supply for the primary part of this computer. Both of these are made by Data Power Incorporated. And this one nicely has actual pinouts for everything. 5.1 volts, minus 12, plus 12, plus 12, plus 5. Yeah, it looks like pretty standard stuff there. Although this part down here is 300 volts DC output. Not sure what that's for. V-bias, shutdown. Looks like to get this out, you can loosen these screws here, slide this up. These are slotted, and then perhaps that kind of pops out. And this power supply here looks like it comes out in exactly the same way. Now, looking at this hard drive down here, we can see the bottom of it. It's a little bit concerning because it said it was SCSI, but we're looking at what looks like an MFM connector here. So there's probably an interposer board that goes between this and the main motherboard. And the main motherboard has a SCSI interface, but you need that interposer board to convert the two. Now, luckily I have a way to archive MFM drives. So I guess the first thing we need to do is get this thing out of here, which looks like you could just release these screws and probably goes out that way. I gotta find that interposer board though. I want to try to archive it with the interposer in place. And if all else fails, I'll hook this up to the MFM emulator and then I should be able to dump this as well. Now I'm looking way in the back there and there's sort of this beige thing there, and that might be the interposer that is converting the MFM drive to SCSI. And looking at the motherboard, we have the SCSI interface here, and that definitely is not MFM. And the 50-pin ribbon cable is visible there, and it kind of goes down. So it looks like the interposer is behind the motherboard, which means I might need to try to take this out of here. When we look at the key lock and the switch that's behind it, this should be no problem at all to bypass. We just have to kind of figure out the pin out of how this all works. And luckily, when it comes to the LEDs for this front panel, they're just sort of pushed out of position. That's why I didn't see them when I was looking through. There we go. Now they're back in position. Now looking at date codes on these ICs, I am seeing 28th week of 1984. There's stuff from 1983 on here and a bunch of stuff from 1982 early on. But the dates kind of go all over the place. But the fact that that says 85 on that chip that is soldered on, that means that this board was almost certainly built in 1985 or after. As you can see here by these wires, there's a serious amount of rework that's been done on this. And they did a nice job though. The wiring is meticulous and really well applied. There's glue holding it down in the right spots. Up here, you can see a bunch of it, just very meticulously applied. This chip here is a little haphazard. It's in a socket. Whoa, the label just fell off. It's a PAL chip. I'm just gonna get a piece of tape and stick that back on. But the bodge wire that's going to that chip, which has several legs that are lifted, it's all a little sketchy. So I'll just put a little tape on there to hold that label back on. So looking closely, we do have signs of corrosion right here around this clock battery. Very unfortunate. There's some green stuff on those resistors there. A few traces don't look so great. It's very minor. It doesn't look, it kind of went down on these chips just a little bit, but everything over here is completely fine. It's just in that one little area. Let's see if we can get this out of here. There's a thumb screw on the motherboard. I think this might slide out potentially, slide forward. Okay, with that out, it's captive. Does this move? There are some push pins here. I wonder if those need to come out. I think those are holding, I think they're holding the RAM card on, so I'm not sure those actually need to come out. I'll unplug these connectors on the top here. Oh, and I just realized there's another one of those thumb screws right here. If that's all it takes is 2 thumb screws to slide this out, that's very nice and serviceable. Now, does it slide? It does. It has some notches on the top, so I can lift this up and out. So that's one big logic board. And let's flip this over so we can look at the RAM card on the back. There's the RAM card. Interesting is theoretically you could have more than 2 megabytes, but this obviously is just 2 megs with these 256 kilobit RAM chips here. So 256K, this is 512, 1 meg, and 2 megabytes with that memory. Thank you very much, Plexus, for putting all the RAM in sockets. At least I'll be able to take them out pretty easily for testing purposes or whatnot. On the back here where the battery is, this looks okay. I don't see any corrosion, nothing too bad. There are these large pins here. I assume those are kind of sockets. So I think this battery is actually not something like a Dallas where the chip is inside the epoxy. I think it's literally a battery, and these pins probably supply the charging current to the battery module itself. So that means we can take it out and hopefully the computer will still work without the battery, and then maybe we can just supply it with a little bit of a CR2032 for when we actually power this up. With the motherboard out, we can see that the hard drive is right here, and that's the power supply module, and there's another one right here. And definitely behind this is the interposer that goes from MFM to SCSI. I can see the MFM cables coming in down here, and SCSI comes out on the top. So I popped these 2 covers off the back, and that gives us a little bit more view into that interposer there, but I don't quite see how to get it off. It uses a normal Molex style power connector right there, but something is holding that on. Part of me has me wondering, do I need to take this power supply out? And I have loosened the screws, but it is really heavy, or All these cables in here are really holding that in place. Okay, there was one more thumb screw on the power supply. Seems that the mains IEC input is attached to it. And with that, I was able to lift this up and get it out. Well, I haven't got it out yet, but I was able to lift it out. Let's see what we can do here. This thing is pretty cool how it's designed, but it's also a little unwieldy in some ways. With this tilted out, you can see the interposer. Looks like this is held on maybe with a little tab right here. Let's pull on this. I'm pretty sure this is some kind of a push pin situation. Oh, that is really stuck though. And as far as that little push pin goes in there we go. I used a tool to pull that out. Put the power supply back in there. Just needs to kind of sit in there. Looks like the interposer is made by OMT Incorporated. OMT IE9, but I can see the brand name down there on the bottom edge. It's actually a floppy drive controller and a hard drive controller. There's a regular NEC FTC 765, and then those are the data cables for the MFM hard drive. So the 6810 system, as it's addressing the floppy drive, is doing it through this SCSI interface. So next, I gotta get this MFM hard drive out, slide these off, get the screws out of here. We'll just loosen them up first. I'll take the top two out last. All right, the hard drive, I'm just gonna hold on to it while I get these top screws out. The case design actually has a little retention mechanism in there so the hard drive doesn't just fall out when you take the screws out. That's kind of nice. There are some really thoughtful touches put into this case. This bar right here is what I was talking about, holds the hard drive in. So I gotta unplug the Molex power connector for the hard drive. Just slide it out the front. There we go. Full height MFM hard drive. A big beast. Made by Fujitsu Limited, part number B03B-4805-B003A. That's quite the long model number. Date is 1985-9, so 9th week, I suppose. I have the motherboard on the bench. The reason why I have this paper here is because the stickers have fallen off the EPROMs there. So before I take those out, I'm just gonna cover that up. So when I was first looking at the machine, I noticed that this panel seemed a bit loose, and it turned out that one of the tabs was actually snapped off. So last night before I went to bed, I actually got out a little JB weld and I epoxied that back together. So that way, well, when we put it back together, this thing won't be loose anymore. I also went ahead and disassembled the front switch here with that key lock cylinder, which I think I am gonna have to drill out. Now I could just jumper these wires here to get the system to turn on, but the way this works is there's two micro switches right here that get pushed on when you turn the cylinder. On the back side here, when you turn the key, it actually pushes these little plastic pieces here which line up with those micro switches. So I think the easiest thing to do is just mount this in a vise and I'll drill out those pins. I don't have any skills to pick this lock, so that way I could just turn this with a screwdriver or any other key. What I want to do in the rest of this video is I want to dump the EPROMs that are on this board. There are 4 here, and I want to dump the one that's on the SCSI interface board as well. And then I want to take this battery off here. In fact, let's just do that right now, because I feel that we should probably start cleaning up the corrosion that's going to undoubtedly be underneath this thing. Oh yeah. It's probably a NiCad battery inside there, judging by the green crusty corrosion. And on here, yep, same thing. A little bit of green crusty there and there. So let me clean this up. Let me get rid of this zip tie first, and then I'm gonna clean this up. So I just first sprayed this with a little bit of IPA, and luckily the corrosion is very minimal. It's not super bad. Obviously these 2 terminals have some corrosion on them. Well, all 4 of them have some corrosion, but I don't see any broken traces, at least not initially. I'm gonna hit this with a little bit of vinegar just to see if this reacts at all. See if there's a strong base there with that corrosion. That's what the corrosion is from these types of batteries. It's this very strong base. In case you are curious what this is, it's a Data Sentry from GE, model number DS3SD. Nickel cadmium battery. Yeah, bad. Luckily it was mostly sealed up. Okay, so I have some vinegar inside here. It looks black because there's some spray paint on here. So I'll just put this on a cotton bud here. And we'll wet the area, and I'm not gonna wash this whole motherboard. I just wanna wash this one little area, and I can put IPA on it afterwards just to wash this vinegar off. Luckily, I'm not seeing any kind of strong reaction. There's no bubbling or anything. So I think the IPA probably washed off the majority of what had leaked onto the board. Now, while I wait for this vinegar to soak in a little bit, I can see here an MC1468 18P. That is the CMOS battery. It's a very standard chip used on all sorts of PCs and whatnot. In fact, you can just replace this entire thing with a Dallas type clock or one of the modern replicas, And then you don't need to worry about even installing a battery because of course the modern replica will have its own battery. I did a very similar swap on my PC 5170. It's an IBM 286 board. And I also did it on the BBC Master 128. And yeah, I swapped this chip out with the modern replacements from Necroware. And that way I wouldn't have to worry about any batteries in the future. Okay, I think I've cleaned this up about as good as I can. I let that vinegar really soak in, then I washed it all off with IPA. A bunch of the green corrosion, at least from those two pins there, did come off on a paper towel, but the rest of this looks in pretty good shape. I don't see any corroded traces, although it's possible. There's some that look a little bit dodgy, but should be easy enough to fix. As far as the lock goes, I was successful, but it was very destructive. The entire thing kind of blew apart. And I do have it with some glue on there right now. That's why it's clamped. Let's see if this still turns. It does. I'm kind of concerned that the glue is gonna lock the cylinder, but now we can turn this. And if you look around the cylinder, see there's a little pink looking pin there. And if I turn this, then a white pin is gonna appear. And those are what push on the micro switches to turn it off and on. So now a key is just a screwdriver or any other key that fits in there. So now I'm just going to spend a little bit of time removing these EPROMs one by one. I'll put them back in the board so I don't mix them up. And I'll also pull the one out of the SCSI adapter here, and I'll upload those along with some photographs of this to my GitHub. There'll be a link in the description. On the motherboard, there were 4 total ROMs. They were 27 128s. And since it's a 16-bit system, there are high and low byte ROMs, and I merged those together and we ended up with 2 files, U19 and U17. Let's start with a U17 merged file. I have a feeling this one is for the program processor or whatever the main one is that user processes run on. If we scroll through this stuff here, we will end up where there are a whole bunch of strings. Unknown device, bad offset, unit specifications, unable to wake up disk controller, bad disk read, invalid disk init block, unable to wake up tape controller, bad tape init, bad tape read, bad tape seek. What's fascinating here is that it looks like it's actually able to read the tape drive into BIOS routines or whatever, like the ROM routines here. So it's not just an OS thing. I shared some of the stuff I've been finding with this computer with my patrons, and one of them mentioned that there was a Sun Microsystem computer that was from the 80s, around the same time as this machine, and it also used an internal SCSI tape drive and a hard drive, and that user told me that it actually booted the system from the tape drive, and if you needed to recover the system, you'd actually boot the main OS off the tape, and then I think it would reinitialize the hard drive or whatnot. And I'm wondering if this Plexus thing actually works the same way. Continuing on, we have unix.pt, sys5.pt, format.pt, make file system, restore, file system check, file backup. They all seem to be pointers that maybe point to these particular utilities. But here we are with a boot string, Plexus primary boot, revision 1.2. Looks like disk, boot disk not formatted, boot unknown controller, boot phony SCSI address. That's a phony address. Looks like there's some kind of routines in here to actually format a floppy disk. Yeah, it looks like it. Bunch of drive errors and things like that. Records not found, write protected, correctable data field error. Just all sorts of system status related stuff. And it looks like we have exited where the strings are. So we'll just kind of zoom through this. I think that was generally it. Oh no, here's a little bit more at the very bottom here. We have a bus error, address error, bad trap. This is almost like some kind of diagnostics thing. Some more SCSI stuff, bad controllers, SCSI registers, TTY command, halted. That's the last message. And we get 0, 1 through F for some hexadecimal conversion routines. And that's it. That's all that's in this ROM file. Moving on to the U19 merged file, this one starts out right here with RD32, and then there's a date, June 4th, 1985. There is a little bit of text in here somewhere. There's some diagnostic routines that I found looking at this earlier. Here it is. Self-test, revision 3.3, self-test complete, self-test failure. And it looks like maybe these are some of the messages here, proms, statics, SIO, stuff like that. So maybe the IO controller outputs this immediately over the serial port when you first power on the machine, and then it hands it off to the other ROM for actually booting the system. I wonder if this is a kind of RAM test here. Address something something, received something, expected something. So this might actually be telling us if there's a bad bit, for instance, with what's written to memory and then read back. That could be helpful. Interrupt received, it expected something else, received, expected, timeout, monitor. And the last message in here says failed, no boards. I did also dump the ROM that was on the Omti SCSI controller. I don't think there were any strings in here. I took a quick scan. I know I'm not using a strings command, which would quickly identify any strings. Potentially inside the SCSI controller, the only thing we might have is like the brand name showing like the SCSI response from when you query this unit. Because of course, SCSI does show a brand or a drive or whatever when you query. And I didn't see anything in there. But at the very bottom here, it does say right here, 5200 VE. And my assumption is this is a date, August 28th, 1985, although there's an extra 9 there, so not totally sure. And that dovetails into the interposer that's in this thing that converts the ST506 MFM style hard drives into SCSI. And I was able to find the actual manual for the interposer, and it's the Omti 5000 series SCSI Intelligent Data Controller. And remember that string in the ROM file said it was the 5200. So let's look in here and see if that's an actual model number. Oh, yep, there it is. Omti 5200, Winchester, and floppy drive, which is pretty much what I already figured out. In this circumstance, a Winchester is the actual hard drive itself and floppy drive interface. And it looks like they had versions for tape and floppy. Now, what I'm curious about with this interface is the number of heads and cylinders fixed inside the controller, like in that ROM that's on there? Or is this something that it figures out on its own? Or is it something that's configurable from the host system, like via a SCSI command? It says here it supports drives up to 65,000 cylinders and 16 heads. So that's far more than hard drives at the time this thing was released, which was 1985. Now this Omti interposer uses a Zilog Z8 microcontroller, which is kind of like a Z80 processor. I think the instruction set's pretty similar. In case anyone's going to try to disassemble the ROM that's on the Omti board, then make sure you set the architecture to Zilog Z8. The reason why I'm concerned about this heads and cylinder thing with the interposer is the battery that was on the computer obviously is bad. So we've lost the equivalent of the CMOS settings. And if there was something set in there that then went and configured the heads and cylinders on this SCSI interposer for the drive to work, then potentially the system is just not going to boot, even if the drive is working, because we've lost those settings. And so far, I haven't seen anything to say that this thing auto-configures itself based on the heads and cylinders, because that is theoretically possible. It could do a little process to do that. So I'm looking through all the commands here. Looks like tape commands. Look, assign disk parameters. And there it says for the Winchester or the floppy drive. So that might there be the command to actually configure that interposer for the hard drive specifically. And I'm assuming because it says in the paper that you could have 2 hard drives, for instance, in this thing, that it supports larger hard drives than the one that was actually in there. I looked up the heads and cylinders for that drive that we took out of that thing, and the capacity is only 68 megabytes formatted. But remember, it says right here that the maximum capacity that the Plexus computer supports is 152 megabytes, which actually is kind of curious now because it shows formatted capacity as 76. But I think that this drive is 68, but I actually did find the original brochure for it. Here it is. This is that Fujitsu drive. There are a whole bunch of different versions of it in different sizes as well. And I think the one we're dealing with here is this one, M2243AS, where the formatted capacity is 68 megabytes, which actually matches what it says right here on this list. But the unformatted capacity is 86. Okay, so that maybe makes sense because that formatted capacity is probably for MS-DOS, and maybe the way this formats the drive actually results in 76 megabytes. So back to the Omti controller manual, looking for stuff to do with configuring the drive. There is some jumpers on here that let you set the bytes per sector. And here we go, default parameters. Winchester hard drives, upon power on or any reset, the controller defaults to the following parameters. The byte numbers and hex values refer to the parameter list. Step pulse width, number of heads 4, cylinders low and high, 153 cylinders, and number of sectors per track based on jumpers. So, okay, so it's defaulting to a drive with only 153 cylinders and 4 heads. That's going to be maybe like 5 megabytes. And the reason why I say that is 153 times 4. Yeah, a Seagate ST255 is exactly 615 cylinders, 4 heads, and that's 20 megabytes formatted. And this seems to default to some drive that is just a 5 megabyte in size. Maybe it's just a safe value. And continuing on, it just seems to talk about other stuff like disk drives and things like that. Yep, and there we are at the bottom. So there's absolutely nothing about setting the parameters and then saving them. Now, the only thing that might be possible is maybe once you set the parameters, it saves it to some part of the disk, like the very first sector. And then next time you power it up, it should read that sector back and configure the interface. But I'm doing another scan through the manual. It doesn't say anything about the fact that the parameters can be saved. It just seems to say you have to use the assign disk parameter command. And I'm assuming that has to happen every time you power cycle the system. I'll worry about the whole drive type parameter stuff when I actually get to the point of turning on the computer with the drive in there, if we even have a working drive. I think I'm really counting my chickens before the eggs hatch here, because honestly, the drive might be totally dead as it is. MFM hard drives are notoriously unreliable. And if that drive is, well, not working anymore, well, I think there's really no hope for ever getting this computer working beyond at least seeing that diagnostic stuff when we power it up. So to that end, I'm going to stop putting it off, and it is now time to try to actually power up the hard drive from the machine. This is not one of them. This is my hard drive MFM emulator. And the cool thing about this is not only can it emulate hard drives, and that's what these connections are for, but you can plug an MFM hard drive into it, which I have this Seagate ST225 plugged into it, and then you can archive or image the disk onto the BeagleBone. And this has a BeagleBone underneath here, which has built-in memory, and I'm connected via Ethernet over SSH. The idea is you analyze and you recover the drive onto an image, and then you can restart this in emulation mode. And then I would be able to plug the SCSI interposer into these connectors here, and then this would actually emulate the physical hard drive. It wouldn't need that drive anymore. And of course, we then have a working image, which I can copy over Ethernet to, a modern computer, and we can analyze that and see what's on there. Now, the reason why this is hooked up as it is here is that I always forget how to use this thing, so I had to refamiliarize myself with the commands and whatnot that this uses. And I was using this untested Seagate ST225 to actually test the archiving or imaging abilities of this device. So what you see on PuTTY here is me actually trying to image this Seagate drive. Now, one of the things about this drive, and I've never tested this one, is it seems to have a problem on head 3. So as I was reading through, there were all sorts of issues. Now, in the end, it gave me a summary of what happened. It expected to read 41,820 sectors, properly that is, and it actually got 41,216, which meant we had 599 bad data, and I guess 5 with bad headers. So there's a whole bunch of bad sectors on this drive, and they all seem to be coming from head 3. Scrolling back here, you just see there's like tons of errors. Now, a lot of them do recover. Well, sometimes it doesn't. Bad sectors, and it tells us which sectors are bad. But other times it says all sectors are recovered after 1 retry or 3 retries or whatever. So even though there were tons of errors, in the end, well, 600 bad sectors, not great. But on this hard drive, we're able to read the image that was created with this device. So we can look at the partition table here with fdisk, and it looks like we have one FAT16 partition. Now, one of the problems is this is a drive image of the entire thing, including the partition table. So I don't think there's an easy way for me to mount just that one partition that's visible right there that starts at sector 17. But another program that's actually kind of useful is this thing called FATCAT. And this thing allows you to specify an offset. And if we look at the number of sectors that the partition starts at is 17, you do 17 times 512 for the sector size. That gives you 8704. And this allows us to actually list what's on this hard drive. And there it is. Like, I never hooked up this hard drive to a real PC, but we can actually see what's on here. WordPerfect, Lotus, some games, Lotus 123 again. SpinRite was run on this thing at one point. There's Park Command, a screensaver, label, just random typical PC XT stuff that's on here. Now, another thing that's super awesome about this particular emulator is it understands many different formats for MFM hard drives. The thing about MFM hard drives is that the format that's actually on the disk is specific to the type of controller that you're using the drive with. An ST506 style hard drive or MFM hard drives are pretty dumb devices, and that means that the controller writes the bit stream directly onto the disk or reads it back. So unfortunately, that means one controller to another is totally incompatible. Now, it's not to say you couldn't just take an MFM hard drive that was used with a different controller, low-level format it, which sets a new base format down, and then you're going to be able to use it just fine. But if you're hoping to recover data off of it, well, then you need to understand what kind of controller made it so that you can make heads or tails of the format on the disk itself and decode that. Now, what's really cool is that this MFM emulator supports an absolute ton of different formats. And these are just some of them here, like Superbrain, Western Digital 1006. This was the format that IBM created for the IBM PC 5170, the 286. So pretty much all 16-bit MFM controllers that are modeled off of the one that was originally in the 5170, I'm pointing to the one over my shoulder here, they all use this WD1006 format. In fact, this hard drive here, the one that has the bad sectors, when it started analyzing and then dumping all the data off of it, it said it was that particular format. But as you can see, we have a ton of different formats here. Another couple Tandy formats. There's a Motorola format here. Acorn had a format as well, Electronica. But if we scroll through this list here, there it is, Omti 5510. I'm assuming that's the format used on the 5510, the 5520, and the 5530. And we have a 5520 here. So that means that this thing should easily be able to decode the format that's actually on that disk if it works. Now, the best of my understanding is if you're using a format that's not understood by this, it still can image the drive and then emulate it because it just is emulating the bits, right? But when it comes to decoding an image file that you could then use, say, with an emulator, that's where it needs to be able to read the actual format. And it's pretty cool that this SCSI interposer is one of the ones listed here. I think I have delayed things enough. Let's plug this into power and first of all, see if it even works. So I'm just gonna reposition things here a little bit. I'm gonna power off the power supply. Notice there's a red light on there. It's because it has supercapacitors, so that thing is able to stay running even after you turn it off. The very first thing we're gonna do is we are gonna power up the power supply without the data cables connected. We just wanna see if this thing spins. I'm gonna put my microphone right next to it so you can hear exactly the sounds that this thing makes. Okay, so obviously it's spinning properly, but I was expecting more head activity sounds, and it doesn't sound like it's doing anything. I'm gonna power it off. Yeah, I didn't hear any head noises at all. I will connect up the ribbon cables here, and we'll power this back on again. Takes a moment to start spinning. I mean, I'm thinking the heads might be stuck. That's what I'm thinking is happening here. The servo speed control is good. I don't know, maybe that's fine actually. Maybe that's the sound of the heads being loaded because there was sort of a chick sound and I don't know. We're going to rely on the tools itself, the MFM read command here, to try to analyze this hard drive. So you don't even have to specify the heads or cylinders or sectors. It figures all that out using the analyze command here. So I'm just going to save this to plexus try1.emu. That creates an emulation file that can be turned into an emulator here, and also an extracted data.img file. So that only works if it can understand that this is the Omti 5100 or whatever. So let's see what happens here. If this can't control the heads on this, we'll know pretty quickly. All right, RPM is a bit high. It should be 3600. Is the light on? The light is on. So this always can take a little bit of time here while it tries to figure things out. But I am a little concerned that it's not going quicker than this. Usually there should be some more feedback. So it did detect that it's an Omti 5510. That's something, and the sector length is 512. But I haven't heard it seek yet, and that is still very concerning to me. Oh, it's seeking. All right, all right. So interleaved, it has 18 sectors per track. You can see there where it says interleaved. And now it's scanning all the tracks. It's looking for the top cylinder. I can look that up. Let's see, what is the top cylinder? Right here, 754 cylinders. Uh-oh. Oh no, bad blocks already. So it found 754 cylinders. There it is. 18 sectors, 11 heads. Whoa, this thing's got massive amounts of heads. So bad block though. Oh, the bad block was set. Okay, that's okay. That means that these blocks were already marked by the interposer board when this drive was formatted. This is different than a read error. This is actually understanding the format of what's on the disk. Oh, we're getting a successful read here. This is excellent. This is absolutely excellent. So it looks like a sector or a track was marked bad and an alternate track was specified, which is what it's doing there. Alternate cylinder assigned to cylinder 734. And this is why it's important that we're using a drive that was made with a controller that this actually supports. Wow, there's a lot of bad blocks set here. I guess this is a large hard drive because it has so many heads. Okay, fingers crossed that this actually works. I'm gonna stop talking and I'm just gonna pay attention now. Okay, what happened here? Found cylinder 0 to 753, expected 149,292 sectors, got 148,680, 0 bad header, 0 bad data, 612 sectors marked bad or spare, 0 sectors corrected with ECC, track read. Okay, okay. I think what just happened is it just worked. We got a good image from this drive. We got a freaking good image. That was nerve-wracking. I was honestly worried that that wouldn't work properly, but it totally did. At one point, when it was reading the drive, it was up near the end of the drive in those 700s, it started getting noisy, like as if the head was moving over a damaged part of the disc, like there was, yeah, it didn't sound good. But once it moved past those tracks, it went back to normal sounding, like just the noisy sound it has here. But luckily, everything was marked out as bad anyways, and they used those extra cylinders up at the top to, you know, reallocate those sectors, and it just works. Oh, wow, okay. All right, so I think at this point, let's turn this thing off. The head parks itself. That is good because that computer was banged around, I'm sure. We'll turn off unplug the power there, unplug this from the emulator. And we'll turn the power supply back on so the supercaps can keep running the emulator. And what I need to do now is SCP the file off of the BeagleBone and copy this onto my bench machine so we can open this up in a hex editor and take a look at the data we see. Oh, you know what? Just for fun, where did that go? Okay, let's see if we can actually fdisk or look at the partition table on this. Okay, so we see 2 files here. One of them is Plexus try1. Now they're both try1. I thought that there were going to be errors. I have to do this multiple times. I accidentally called it try2. The .img is the decoded image, and the .emu is the actual raw data. It's almost like a flux copy of the drive. So if we're going to emulate this, we would use the .emu file, and then the Omti controller wouldn't be able to tell the difference between the emulated drive and this actual hard drive. But for looking at the data, like if we're going to do an fdisk here, we need to actually load the img file. Okay, I'm not going to write this. Okay, no, Linux doesn't know how to understand this. I mean, it's not surprising, right? This is a Unix partition from an operating system that was way before Linux was even dreamed up. So, okay, I just thought we would take a look at that. Actually, let's see it. String seems to be installed on here, so we can do strings on the image here. All right, /Unix. Oh boy, seashells on here, profile. I don't even know like who had this computer or what's on here. Measurable, U-disk. Oh boy, oh boy. Ah, look, here's some more stuff. Message key, SH key. I mean, there's no network interface on this thing, so it's not gonna be telnet or any kind of servers or anything. This thing is completely standalone. Look, there's commands here, alias commands. I mean, I know this is completely run-of-the-mill, but it's pretty cool to see this. Okay, so there's the time zone, PST 8, so here it's Portland, I guess. VT100 terminal, perfect. I got a VT220 that's working, so we can hook this thing up to it. It has mail on here. Who's sending mail? I guess like from one user to another. User/PLX/WBS. We have environment variables for something called qlib, whatever that is. Got some errors and things here. broken pipe, argument out of domain. There are some files here with .c on it. That'd be pretty cool if there was a C compiler because we could actually port some stuff over to this thing. Yeah, a bunch of C stuff here, string compare, string copy. So this might have the compiler installed on it. Yeah, look at this, make file, release, reading internal rules, reading environment. Look at this, System 5, release 2.0, and there's a date there, September 1st, 1983. Looks like we have the contents of a make file here, so it has the C compiler stuff and all the flags and whatnot. You know, one of the things that has me worried here is that we don't know the password. So hopefully this uses like a password file with some like MD5 thing we can just reverse. And maybe we can find it in the disk here and reverse the password out for the root account. Check it out right there. etc password. So yep, it does use a password file. We'll just have to figure out how to find it. Looks like we have password and O password, whatever that is. Password user, yep, that's for changing the password, so old password. Sorry, so many weeks since your last change. Let's grep for root with a colon, because I think that's the format of the password file. All right, so are these the passwords, the MD5 passwords right here? There's a bunch of them. Maybe there's like a bunch of backup copies of this file. All right, I'm gonna have to ask someone to help me reverse these passwords. So when we get the system booted, if it boots, then at least we'll know how to log in as root. All right, well, I feel giddy. I feel absolutely giddy getting a good image of this drive. So we have it preserved, the operating system is preserved, and then, well, hopefully we can get this system booted. I can use the drive emulator if I need to. It's a lot quieter, of course, although that computer has a really noisy fan on it. And speaking of noisy fans, it's time to service the power supplies. I went ahead and removed both power supplies from this machine. So that gives us a lay of the land of all the cables. And interesting is the main power supply actually powers up the hard drive, the SCSI interposer also powers up the tape drive, and the tape drive, turns out it has an interposer as well. The secondary power supply does just go directly to the card cage, and then oddly enough it has one Molex connector that then goes to the floppy drive. I've gone handheld, so sorry about the shaky camera, but this is the tape drive, and here you can see there's an interposer that goes from the SCSI interface to what looks like a floppy drive cable. So I'm assuming this tape drive is more like the type you would find on an old PC. And I just want to point out there's also a set of MFM cables up here, both a data cable and a drive cable, for a second hard drive, though there's nowhere to mount it. All right, so here are the two power supplies, and I guess I didn't realize that there was actually a fan in the primary one here. I thought the only thing that was cooling the computer was the large cooling fan on the back. So all the connectors here do have labels, and it says P7 right there. That is the one that was feeding the other power supply. And if we flip this over, there it is, P7, minus 300 volts DC, plus 300 volts DC. Plus a couple signals here that seem to, well, I guess link the two power supplies together. So when this one turns on, it turns on this other one. Now it seems that the motherboard does have a soft start feature for this power supply, and that's because that key switch on the front doesn't switch AC mains, it has thin little wires going to it. So I have a feeling this remote turn on is actually what powers this entire power supply up, and then that feeds through into the second power supply through this P7 connector. I love here, it says reset in space put, input. So in case anyone is curious, here is the information on the power supply again. So Data Power Incorporated from Orange County, California. Serial number is that really a 252? Is that how low the serial number is on this thing? November 1985, and I don't know, some numbers there if you want to look them up. And our little secondary power supply has some easy to use connections there. These have these little cables here that actually assist you in removing these from the case. Pretty nice little touch there. And we have Data Power Incorporated as well with a serial number of 136, even lower. Customer number 286-1 from May 3rd, 1985. So why don't we start with this one? We'll open this up and we'll see what we see on the inside. I'm going to be looking for leaky caps and of course things like refas. There's not going to be a refa in this one since this runs on DC, but we could still have some bulging or leaking caps, which I will need to address. Also sounds like there's something loose inside of this, so we're going to have to get that out of there. We don't want something to cause a short and cause a little bit of a fire or something. I think those two screws is all it takes. Oh, there it is. Little voltage regulator board there, a couple adjustments available on it. Let's see what falls out of this thing. There we go. I think that was my fault when I took the little grounding strap off that fell inside. So I'm just giving this thing a little inspection. I am looking for anything that looks obviously damaged or burned. So far, everything looks really good. Now this thing is only passively cooled, right? It doesn't have a fan in it like the other power supply. See these flying leads here? These come out of the transformer here, and that's just to enhance the isolation distance between the high voltage and the low voltage side, which is actually probably this side is the high voltage side because this is very close to the input here that comes from the other power supply. So this is the high voltage DC, and this goes into the transformer, and then this is what creates the low voltage DC that this thing generates. Don't really know the voltage rails, but these are two of those Molex type connectors, so 5 volts and 12 volts here. And then that goes to the card cage, which is probably just +5, -5, and +12, -12. We do have a few tantalum caps, these ones right here, so those can go short, but I'm not really seeing anything that looks like it's ready to go. Of course, you never really know with these tantalums, they can just let go at any time, and that will let a little bit of a smoke out. Now with these old style switching power supplies, it's really not a good idea to try to power this up without a load. And that's because this thing does not have the best voltage regulation in the world. It's not using like fancy modern ICs like new ones, meaning it just really needs to operate within a narrow range of load, from a minimum load to a maximum load, just to ensure the regulation is working properly. If you run this without a load, what can happen is the output voltage can go too high and actually cause issues, because these output capacitors here have a limit of the voltage, and I'm just trying to see that here. They are Mallory caps. Yeah, these ones are 25 volts here, for instance, and these two large caps here are 16 volt caps. These are probably used for the 5 volt rail, and these are used for the 12 volt rail. But without a load, it's possible we could get more than 16 volts on the 5 volt rail or more than 25 volts on the 12 volt rail, which would be bad for those really high quality Mallory output caps. These are obviously very high quality power supplies, and I don't see any issues looking inside of here. So this thing is probably just going to work properly. Only thing that kind of sucks is that it doesn't look like you can adjust the voltage regulation without taking the cover off, because there are no holes in this cover here to get to those. Now for testing this computer, I'd say it's pretty safe to say that we could power up the main power supply without this one connected. The only thing is, if we do power this up, we definitely need to remember to plug the card cage in, because remember, there is this board installed in here which just has a ton of power resistors, which oddly has a connector right here to say plug right into this power supply. I wonder if that was how this thing was sold, in that some configurations didn't have this, but actually just had this board sitting inside the case, because there's actually little hold downs in there to hold it, and they plugged the power connector into this. That way all of these power resistors would be in play, because you can notice that this power connector on the back plane looks to be identical to that power connector. All right, now we have the beast power supply here. Got some screws on the side right here. I bet you there's a bunch of these on the perimeter, so I'm just gonna start removing them all. Okay, took those out. Oh cool, this comes off. It looks like you can lift this away, and I think there's a connector for the fan. The fan though is 120 volts. That means it's a really noisy thing. But anyways, wow. So we have another very, very high quality power supply here. Now REFAs might also be in here, but check it out. We got REFAs right here, a whole bunch of them. So these X caps and these are Y caps. We're gonna have to get those out of there. These are big boys. They're gonna stink the place up really bad. This is kind of lame. This cap here is just loose for whatever both of those are. No hot snot or anything. I don't think they're broken or anything. They're just floating around in there. Well, it looks like the fan actually has a power connector right there on that side, so we can get that off, which is good. Let's see if there's any mains filtering in there. No, okay, there's not. That's just the fuse and the high voltage and stuff like that. So we just have to worry about these things here. I'm gonna get the board out of here. All right, we are free. There's the underside. A little bit of marks on stuff on there. Interesting. Just get this little mains box disconnected here. So the cool thing here about what we're doing, we're gonna get those REFAs out, but I can also take this outside to clean it, but I can also check for bad solder joints. I'm gonna warm up the hot glue gun just to keep these two components from flopping around so badly. Anything else that's loose? Everything else seems decently attached down. Now I'm looking for some X caps to replace these two 0.33s, and all I can find is 0.68s and 0.22s. So I'm gonna go smaller. I'm just gonna put 0.22s in there. I'm just gonna do my best and just try to replace them. I have a 0.1 to replace that one. And now I gotta look for some Y caps here. These are 0.015 microfarads. I'm not actually sure I have any of those. I may just need to leave those out entirely. So when you're trying to put new REFAs in, especially ones that are replacing really big ones like this, to get the spacing correct, it's actually easier to do on the back side, and these are just sitting in there. That way I've already done the bending, so when I go to put it in the other side, it'll be a lot easier. Now the things that are most likely to have broken solder joints are these connections here to those connectors. So I'm just going to reflow all of these. And yes, I like to use my desoldering iron. It has a lot of thermal mass, so it works for big thick things pretty easily. Now you can see this like large flood fill thing going on here, and there's a ton of solder on there and there. So there's no issue there. It's usually things like this that just have like a little thin trace that goes to them. Those are the ones that can have issues. Wow, it looks like someone cut a trace right there between those two components. So we'll just fix these things here. Now you just use something like a loop, and I'm just gonna quickly go over this and inspect everything, look for anything that's cracked on here. So I didn't find any broken solder joints, but I found something else I needed to address. See this darkened part of the board here? That just implies that that section gets really hot. You'll notice that right here, this area with this power resistor and these other components, well, there's a couple capacitors right there. Well, I ended up proactively taking those out. These are these two electrolytics, just because anytime you have something that gets super hot that discolors the board, it usually bakes the capacitors that are nearby. Now these power resistors, and there's a couple other around the board like these over here, the board's not discolored there. So they must get warm, but not so hot that it really discolors the circuit board. So always pay attention to parts of the board that have discoloration if there are caps nearby. Now, almost certainly these caps are part of the voltage regulation circuit, and without those operating properly, this power supply probably wouldn't even run. Now, of these two caps that I removed, one of them is this 1000 microfarad cap. Take a look at the bottom. So that was no good for sure. Now this one was right next to that large power resistor, but yeah, that leg just sort of fell out, and obviously it's all baked, it's dried out. Now this other cap here, 22 microfarad, 85 volt Nichicon, it doesn't look like it's leaked, but there's pretty much no way that this thing is gonna work properly. Let's see if this little component tester can test this. I bet it's just gonna say open. Oh, okay. No, look at that. ESR is 2 ohms, 31 microfarad, and what was this, a 22, I think. So that cap actually works. I mean, it's not in the best shape, but I think it definitely needed to be replaced. But we can say for sure that this cap here was dead as a doornail. All right, there's not much else to do here. I put in these 0.22s instead of the 0.33s, instead of these large REFAs here. And then the 0.1 is there, which was in place of the 0.1. And the only thing I didn't replace are these two Y caps here. And I'm glad I took these out, because when these caps get old, they start to leak. And the problem with these Y caps is they're installed between the earth mains, the entire chassis of the entire computer, and one of these goes to neutral and one of them goes to live. So if this becomes leaky, if you're not plugged into a ground fault interrupter or an RCD type outlet, basically the entire computer would start to become live at mains voltage, and you could totally get a shock. Now, of course, what would happen is if this became leaky down here in the basement, I do have GFCIs or ground fault interrupters, so it would detect that and it would trip the breaker. But taking those out obviously is gonna solve that issue. Modern Y caps look like blue discs, and I just don't happen to have any that I could put in here. But I'm gonna operate without those. I'm not recommending you do anything here. I'm personally okay with running without them. But if you're working on a power supply, please replace every component that you take out with the same like for like component. Obviously, don't use REFAs, use more modern ones. But yeah, in place of Y caps, put the Y2 safety caps, and in place of X caps, which are these other ones here, you can use X2 caps instead, which is what I've done here. Well, the power supply is back together. It's time to put this back in the computer along with the motherboard and turn this thing on and see what happens. Rammy's there to help out. So the motherboard is mounted. Both power supplies are back in. Sorry, that's making it out of focus. The rear power supply, which is that one there, that power supply is fully connected. The other one is sitting in there, but it's not connected right now. The interconnect cable between the two is disconnected, so that power supply is not going to do anything. Multimeters are set up here. They are on manual ranging, so hopefully those should show 5 volts and 12 volts. The cables go up into a Molex connector that was unplugged from, I think, the tape drive. The key lock cylinder has 3 positions there. It has a circle with an empty hole, a full circle, and a little dash down here. I don't know what they do. So currently the power cord is disconnected from the back of the machine, but I'm assuming if this is in the wrong position, then the machine will just turn on. And the idea is we're going to power on the machine, and I need to watch the voltage rail to there just to make sure that we are not over voltaging any of the 2 rails. So we'll get the camera positioned so they are visible. And I'm going to go back here and turn on the power strip. Okay, nothing happened. Power strip is on. So I'm going to turn the key cylinder here. All right, something's happening. Got a couple LEDs on the front here. 1 and 6 are lit up. Now all the fans, by the way, are, oh yeah, I didn't even check the voltages, 5.07 and 11.89, so we're looking good. I'm actually gonna turn this off. We'll take these leads out here and just reconnect to the tape drive. Let's turn this back on. I don't know what these lights mean here. I thought that that's 0, 1, what was that? Oh, that was just part of my multimeter probe. 0 was on earlier, and now just 6 is on. Now ideally, I should probably plug in a terminal so we can actually see an output. What's the other position do? Sounds like the power supply makes a hissing sound when it's in that mode. Don't know what the difference is. Let's turn this off again. So I don't know why that looked different there than the first time. Oh, there we go. Both of those lights are on now. 0 and 6. Now I'm wondering if these are some kind of like diagnostics. If we plug in a terminal, maybe there would be messages printing out. I don't know. Let's just let it sit for a second and see if these change at all. No, it doesn't appear that anything is happening here. All right, well, I need to get a terminal hooked up because we need to see if anything is happening. Now, do you think we plug into 0 or 7? I'm gonna plug into 0, see how that works. We're over at the desk here, and I have a serial cable that goes from my bench PC here over to serial port 0 on there. And I'm using a no modem cable. I have it set for 19.2 kilobits per second. Hopefully that's the right rate. We can fiddle around. My lab machine actually has real COM ports. I have a PCI Express multi-IO board type thing with 2 serial and 1 parallel. So hopefully that works. Okay. So what you see there is putty. Let's turn this on. I roll my chair over. Here we go. We certainly got nothing on that serial port there. Nothing at all. So I'm wondering if I should move it to serial port 7. And the reason why is on the front panel, they're all amber LEDs, except for 7, which is green. So maybe that's like the console terminal or something like that. Okay, I moved it to serial port 7. I'm pulling the power cord out here. Let's plug it back in. It moved the cursor a little bit, but I think that was just from plugging in the cable. Well, this is pretty disappointing. I'm just gonna fiddle around, maybe try not using the no modem cable, using the no modem cable. It makes sense you would need to use no modem because we're going from a computer to a computer. Typically, you need to use a no modem in that situation. But maybe that's not the case here. And of course, serial is a bit of a pain because you have the transmit and receive. If you're swapped around, then it's not gonna work. I have been fiddling around with the P20, and I think I've figured out why it doesn't seem to be doing anything. It doesn't seem to be even attempting to boot. Now, I'll just preface this by saying that one time, it actually started doing stuff on the front LEDs. Like, instead of just those 2, it was the green one came on, there was some flashing and changing around of stuff. So I think the motherboard does have some capability to run, but I think I figured out the problem. So the first thing I did is I toned out that front power switch. I wanted to see what the various switch settings did. And what I figured out is the 0 or the O is just off. The wires that go into that switch, none of them are connected together when it's in that position. Then the up and down position for the key lock is, I guess, the on position. And it's the typical, 0 and I for on and off. And what that does is it grounds the remote power on signal that goes into the power supply. So that key switch on the front has 4 pins. 2 of them are just ground. One of them is the remote power on, and one of them is the reset input that goes into the power supply. So when it's just up and down or in the I position, only thing that's connected is the ground to the remote power on. If you turn it to the next position, which is the but it's filled in, that also connects ground to the reset input on the power supply. Now, I don't fully understand what that does. Maybe that's just the reboot for the whole computer, which is why they want you to use the key to do that. So you turn it to that position, and I assume you leave it a second, turn it back to run, and then it just continues operation like after rebooting or something like that. I'm not sure where that switch setting goes into the power supply. Like, why would you need to reset the power supply? I'm assuming somewhere else on the motherboard, it's also picking up that signal and it's, issuing a reset for the whole computer. So during my initial testing though, I had it in the I position, which is the run position from as far as I can tell, but obviously the computer wasn't doing anything. We just were stuck on those two LEDs with no operation. Well, looking at the 4 pins that go into the power supply, and this is labeled on the side of the power supply, we have remote power on, that's when you ground it, it turns on the power supply, and there's a relay inside, so it turns on the fans as well. Then you have pin 2, which is that reset input. It says in space put, and putting this key switch into the reset position does ground that particular input, which seems to be pulled up. In fact, when the computer's off and you plug in the power supply, that pin appears to go up to like around 8 volts for whatever reason. And then pin 3 is an input from the power supply, and it is the power fail. It just says power fail, and I'm assuming this is sort of similar to power good. And then there's a pin 4, which is reset out. I don't know what that does. Maybe that goes somewhere else on the motherboard to reset other things or something. So now I have a base understanding of kind of what's going on with the power supply. I started looking at the actual voltage rails, and I noticed when the system was running, the power supply was kind of making like a hissing sound, which isn't super unusual for switch mode power supplies if they're under a lot of load. But I don't think this thing should have been under a lot of load. The only thing that was really connected was floppy drive, the tape drive, and the motherboard, and the interposer. I had the interposer connected, and yet it was making a lot of hissing noises. So I put the oscilloscope onto the 5-volt rail, and well, it was really, really noisy. We were getting like over 500 millivolts of ripple on the 5-volt line. Now the 12-volt and the -12 looked totally fine. They were just smooth and working properly, but the 5-volt was not looking good. Now that power fail signal also was up at 5 volts or thereabouts. Without schematics, I don't really know if that signal from the power supply should be at 5 volts when everything is working well, or if it should be at ground when everything is working well. I have a feeling that the ripple is probably keeping the computer from even executing. When you have that much ripple on the system, the CPU is just not going to be able to execute code properly. Now it's still around 5 volts, like when I hook up the multimeter it showed 5 volts, but the scope really revealed that things aren't looking so good. Now I was a bit gung-ho with the power supply thinking, oh, it's just going to work. I had those few parts I needed to change and the rest was going to be fine. Well, it appears that's not the case. I have a feeling those output caps on the 5-volt rail are just not working properly. Now the thing is, it could be that there's excessive load on the power supply into the motherboard or the other things on the computer, and that's causing the excessive ripple. But with the system running, I put my hand around the motherboard and I didn't feel anything getting super hot on there. I mean, the things were getting warm just because it's older electronics, but it wasn't like anything was burning hot. There was no smoke or anything. There were no shorts. I did check for shorts with the tantalums. They were fine as well on the motherboard. So it just feels like the output caps on the main power supply are just no good. I have figured out the problem with the power supply, and it was totally a bonehead move on my part. Let me show you what I found. So here's the power supply, and I've gone ahead and I replaced the output caps. Yes, these small output caps are all that it needs. These are 4700 microfarad at 16 volts, that's 5-volt rail. And these were originally 1500 at 25 volts, and I put 2200 at 25 volts. It doesn't seem like a whole lot of bulk capacitance on the output, but that's how this thing was designed. Oh, and one other side note, I found a couple Y caps here. I actually stole them off another power supply, so I replaced those as well. So everything over here is fully replaced. Anyhow, these are the caps that I took off the board. These smaller ones are Mallory 1500 microfarad, 25 volts. These were on the 12 and the -12 volts, and actually those were fine. We'll test those in a second. I don't think those are a problem. But these are the two that were on the 5-volt rail. And remember when I opened this thing up how wobbly they were? Well, yeah, there was a good reason for that. One of the leads had broken off both of these. Like it just metal fatigued right off. So we were operating the computer with literally 0 microfarads on the output on the 5-volt rail. No wonder why it was all over the place. I should have looked more carefully when these were wobbling around versus just putting some hot glue on them to keep them from wobbling. I think everyone wants to see these measured, right? So let's start with these smaller caps, which we know are good. They don't have a marking on them for polarity, but I assume that dot is probably positive. The PCB has markings for polarity, but I also verified because obviously it's pretty easy to install the positive ones. You just go to the ground on the negative side, and then for the negative rail, you have to reverse the cap. So we're getting 1800 microfarads at 0.02 ohms. Yeah, this is a good cap. Mallory makes good stuff. I might actually just keep this because that's a good cap. I shouldn't have changed them, to be honest. Should have just left those on there. But hey, it's already done. The other one here that was on the minus rail, look at that. It's just freaking amazing. Yeah, 1500 microfarad is the rating on these. They're reading even higher than they originally were, but that ESR is super low. Okay, so these, this has a little red mark on the top, but this one has a little bit of a plus thing going on there. So we'll hook the plus lead there, and hopefully I can get this clipped on to what's left of the minus. There we go. I think you have to go lower frequency for it to actually measure. There we go. So it's a good cap. I mean, the ESR is nothing, and we're completely within spec. It's just the lead is busted on it. Oh, it's so annoying. The reason why I never actually tested these off the board is because these Mallory caps are just kick-ass. They're so good. And as you can see, yeah, I mean, all four of these caps are 100% perfect within spec. No issues. In fact, it's probably that these Nichicons I just put on here, which I got from DigiKey, are probably going to fail before these things actually fail. It just sucks they didn't put down a little hot glue. That would have kept the lead from breaking on this. That just sucks. All right, the power supply is back in the machine. Everything is re-hooked up, including all the drives and stuff like that. I don't have the second power supply hooked up still. This is connected into the Molex connector, so we can switch the mode of this to actually look at the voltage. 5-volt rail, of course. But I also have the oscilloscope clipped on to the 5-volt rail, so I can look at how clean that is. So I'm going to plug the power supply in. So that is plugged into the mains. Of course, the switch is off. Let's see, the power strip is turned on. So here we go. Let's turn this on. Oh, tape drive is making a bunch of noise. So we're getting the good LEDs there. The green one's on, plus one of the other ones. Yeah, 5-volt rail there. That looks much better now. If we switch the mode here, 4.95 volts, we have a nice solid line. So that looks good. Far better than the noisy garbage we had before. Ooh, check it out, check it out, check it out, check it out. The LEDs are doing stuff. Blinky, 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 blinky. Oh, this is a good sign, everyone. So that power supply was causing all the issues here with this, but the blinky blinky here, I cover that so you can see the blinky blinky. That's what we want to see. That is what we want to see. Okay, what I'm curious about now, that power fail signal that was over here on the connector, it was pin 3, is just at 3.5 volts. Okay, this is still blinky blinky over here. Yeah, I don't really know what that does. Oh, let's try the reset. So I'm gonna move this into the reset position. Okay, it stopped. And we put it back there. Okay, I don't know what that did. Maybe it just put everything in hold or something. But let's pull that off there. Oh boy. I have it connected up to COM 0. Let's turn it on and let's hope we see some activity there. If the baud rate's wrong, we should at least see some garbage there. Oh, okay, the lights are blinking. They're doing stuff. We're not seeing anything. Well, there was just that one little letter there, but maybe that was there already. Now again, this could be the same thing where I might have the transmit receive reversed, or I'm on the wrong COM port. All those lights are blinking on there. They're doing stuff. I switched it over to COM 7 and I'm not seeing anything there, so I'm gonna do the off and on thing here. Looking over my shoulder. Certainly nothing happening on there. Nope. I'm gonna put it into that reset mode or whatever it is. Makes all the lights stop blinking, so that's something. As soon as I go back to the middle setting, they start blinking again, but nothing on the COM port. I'm just going to reset the terminal just in case. So oddly, I hit enter on the keyboard and the tape drive was making noise and all the lights stopped blinking on the front. All that's on now is 7 and a couple of the other ones, but the tape drive is making kind of like tape noises. There's obviously no tape in there. Maybe this needs to be at 9600? I don't know. We're making progress. It says Plexus. That's coming from the machine. Now I'm on serial port 0, but the thing is the pinout is completely non-standard. So I was using the oscilloscope to kind of look to see which pins had something going on, and it's pin 1 that's outputting this, and the ground pin is also something completely unusual. And I have a serial port set to 9600 bits per second, and the flow control doesn't matter because it's not even hooked up. And that is showing Plexus. So let me go try to do the reset and see if that says anything. I know you can't really see me, but it's noisy over here. So it's in reset now. And I turn it off and now it just says Plexus. Let's turn off the power altogether. And we'll power back on. Now it just says P, Plexus. Okay. Weird, very weird. So I turn the machine off and on, and now it doesn't boot at all. It's just doing 2 lights and 1 is kind of dim. It's kind of what it was doing when the power supply was messed up, but I did check all the rails. They're all perfect. There's no excessive ripple. Everything looks good on the power supply. So there's definitely something going on with this motherboard here. Maybe it's just a matter of reseating every chip, but I think what I'm gonna do now is take a break and I'll see how this is in the morning. Now that we have the serial board hooked up, if it does display any text more than Plexus, we'll see it. And maybe that'll give us a clue as to what's going on. I was just shutting everything down and I pulled the plug on the computer and I just happened to plug it back in. And look, I noticed the pattern on the LEDs was different and it's showing the self-test message. So this absolutely confirms we're stuck in a boot loop. The problem is, I don't even have a manual. I don't even know how it's supposed to work, let alone schematics and that incredibly complicated board. So the only thing I can think to do, and I'll work on this tomorrow obviously, is just take every single socketed chip out, and there are a number that are socketed, and put them all back in with a little Deoxit. And maybe take the memory card off, put that back on. I don't know. I would hope that if the RAM were bad, for instance, that it would tell us that. This is not reassuring what it's doing right here in a boot loop. Also, we could have some damage around the battery area. Maybe. I don't know. Anyhow, this is a problem for me tomorrow. So the fact that it got a little further here means that maybe tomorrow we'll see some more message than just that. Welcome back. We have the broken P20 here. Now I've given a lot of thought as to what was happening last night, and I've come to a bunch of different conclusions that we need to follow up today. First off, I noticed that the power supply, which is on the other side of this motherboard of course, the fan is not working on the big master power supply. Now the funny thing about it is I am positive that I reconnected the cable to it, and I watched the footage that I shot yesterday, and while the power supply was apart, I actually spun the fan. So the bearings aren't bad, there's something else that's failed inside there. So I noticed this because when I was sort of cleaning up and putting everything away last night, the whole power supply was super hot. And I'm wondering if that maybe has something to do with the issues that this machine is having. When I had this thing powered up last night, it was just continually rebooting. When this computer had been off for just a couple minutes and I turned it back on, the pattern of the lights on the front of the machine looked a bit different, and then I actually got that full banner about the self-test. It's my assumption that something in the motherboard, or maybe it's the power supply, is causing the motherboard to just continually reset. And you know, when I turned it on, it said like P, 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 and then it started saying Plexus and that kind of thing. And the lights on the front of the machine as well were just sort of flashing all in unison. I think that was the reset cycle that this thing was stuck in. I already know for sure that when you turn the front key switch to the reset position, that actually sends a signal to the power connector onto the reset input signal that goes into the power supply. But then there's a reset output signal, pin 4, And that might go to a reset circuit on the rest of this motherboard here. And I didn't dig into that at all. So that's something we can do today. If the computer is still stuck in that boot loop, then I think we need to take a look at the reset pin on the Motorola 6810s. That's pin 18 on both of these, and see if that is cycling over and over again. Now, of course, the first thing to check would be that pin 4 on the power supply connector, that reset signal that comes from the power supply, and see if that is cycling as well. It could be that the overheating in the power supply was just simply causing that reset circuit to trigger over and over and over again to keep the computer from operating. I also gave some more thought to the serial port situation. Remember how I said that the pins it was using were non-standard? I think for 9-pin serial, there really is no standard, and what we consider a standard today was something that was commonly used on IBM PCs, so it kind of became a de facto standard, but there really wasn't a standard, and I figured out last night that the pinout for the serial port on this, at least the 9-pin ones, is not the same as on a PC. I already know what the transmit pin is from this machine sending data out, I already know what the ground pin are, but for us to control the machine, we have to figure out what the receive pin is on this motherboard. And I talked to my friend Pat, and he gave me some really good tips, which I've gone ahead and followed, and I think I figured out what the receive pin is. Let me show you what I figured. These are the 9-pin serial ports on the back of the computer, and this one is serial port 0, and that's the one that we saw data on. So we know that's the one that's relevant for this system as it's booting up. This 48-pin package right here is a MOSTEC SIO chip. I went and looked up the datasheet for it. This chip interfaces to the CPU and provides 2 serial ports. This doesn't provide RS-232 signal levels, it just provides the protocol for RS-232. You'll then need some signal transceivers or signal transmitter and receiver chips. And that's what these chips are right here. This one that's a white color here, this is an MC1488. And this chip right here is an MC1489. The pinout for the MOSTEC shows that this thing has 2 full serial port support, including hardware flow control. And that does make sense because we actually have 4 of them on this motherboard for the total of 8 serial ports that we have. And then the 1488 and the 1489 each have 4 buffers each in them. One of them is for sending data over RS-232 at the correct levels, and the other one is for receiving those levels from something that's plugged in externally. Even with 9-pin serial ports like that's used on this thing, you typically have 2 pins for receiving and transmitting, RX and TX, and then you would have 4 or 5 hardware flow control signals, with 2 of them going out and 3 of them coming back in. If hardware flow control were fully implemented on these 9-pin ports, you'd pretty much need an 88 and an 89 on each one of these serial ports to handle all those flow control signals. But that's actually not what's happening here. It looks like you have 188 and 189 and another 88 and another 89 for all 6 of these 9-pin ports. Down here where there's 25-pin ports, we actually have additional 88s and 89s, and that is making me think that these have actual flow control signals in them, but the 9-pin ones do not. I ended up using my multimeter and going from this serial port 0 here at the top and toning out each one of the pins going to the 88 and the 89. And I was able to ascertain that only transmit is connected to the 1488 on pin 10 and receive is connected to the 1489 on pin 4, and then ground is connected, and that is it. Everything else is not connected. In fact, a couple of these pins are actually cut. Like they're not even there on the 9-pin, but the rest are going to the motherboard, but they don't appear to go anywhere, at least not that I can find. If hardware flow control were implemented like RTS, CTS, then those signals would be going to these buffer chips, but they're not. And I have a feeling for this 1488 transmitter here, it's probably serving all 4 of these ports here for the TX bit, and this one here is doing the RX bit for these, and then that one probably just handles those 2, and the one down here handles those 2 with a couple extra pins that aren't used. I didn't fully tone these out, but the 25 pins do appear to be using standard DB25 RS-232 pinout, where pin 2 and 3 are the transmit and receive pins, for instance, and it does appear that some of the flow control signals are going through to the transmitter and receiver pins. And you could actually figure out which pin is what, like what's going to what flow control pin, by simply looking at the in and out buffer on these chips and then tracing them back to the equivalent MOSTEC chip down here that is handling the serial port. It'd be this one at the bottom probably handling these 2 25-pin connectors. I am super confident that the DE pin 6 is the receive pin, so I can send data into this from my lab computer, and we can actually send commands to this thing. So what I did is I took a couple of these adapters here, which are very handy, I must say, and these are just DE9s here, and I wired them up appropriately. On one end is the IBM PC standard for RS-232 9-pin, and on the other end is the standard that this computer is using. So with this and the null modem cable that I'm using, we should have full control of this computer if it actually boots up. So with all that said, the very first thing I'm going to have to do is take that power supply out for a third time and try to fix the fan. I'm probably just going to replace it with a 12-volt fan and wire that up somewhere into the DC side of the power supply, and then at least that poor power supply won't be overheating. The fan has been replaced. As you can see, this one spins very nicely, but yep, doesn't work. So I put a 12-volt Noctua fan in the computer. That's all I had sitting around. It's a little quiet, maybe not enough airflow. Hopefully it's enough. What I want to do is turn this thing on just very briefly. I have the big noisy case fan disconnected. That's a 120-volt fan as well. I just want to make sure that that Noctua fan in there is spinning. The key switch is currently turned on and the mains is connected, but the power strip is off. So I'm just going to turn on the power strip and I want to listen for a working fan. Yes, we have a working fan. I heard it blowing inside the power supply. So that is good. Hopefully that will keep that power supply nice and cool. All right, with that problem fixed, now it's time to hook the serial cable back up again, turn this thing on, and see if it goes into that reboot loop again. And if it does, grab the multimeter and we'll start probing around on the motherboard, which is why I have the computer turned with the motherboard facing out. All right, we are ready to go. And unlike last time, I decided to use OBS here to actually show you what the lights look like while we can look at the terminal. Everything is all hooked up, including the transmit line. So if this thing does boot, I should be able to actually type here. So we're ready to go. I'm procrastinating a little bit because I just hope it doesn't go into that reboot loop again. I'm gonna roll my chair over here and turn on the power strip. All right, here we go. Okay. Why am I not getting anything out of the COM port though? You can see the lights there. Okay, one of the differences is I was using an extension cable on the serial port because it didn't all reach. I guess this extension cord was not a straight through cord or something. I don't really know where this came from. Let's not use this. All right, so now the view you're getting is of the back of the computer where the serial port's connected. I know that's a little bit boring, but sorry, I just can't make it all work with the computer turned around like that where my cord reaches. Okay, here we go again with the power strip. Nothing. Oh no. Oh, that's not, it's working worse. So I looked at the front and the lights definitely are blinking, not in the rebooty way, but in the I should be working way. In fact, the tape drive is doing noises and stuff like as if it's trying to boot. But why are we not seeing anything? What just happened? I hit enter and okay, so the system is working. I wonder if I just have a bad connection on my little like dongle thing that I set up. Well, okay, so I took a look at the front LEDs. All of them are just solid on, no more blinking. So I guess that continual rebooting was the power supply overheating. I don't really have any other explanation for it other than that. And maybe there's some kind of a chip in there that handles the reset circuit and it was just getting too hot and causing it to constantly reboot. Okay, so we're definitely working. Plexus primary boot, Control M. Control J. I'm pushing letters and you know what, I don't think this is actually getting through. I'm going to reboot the computer and let's see if we can watch the entire boot sequence. So I just did the reset by turning the key back and forth, and this is what we weren't seeing yesterday. Self-test revision 3.3. Right. SC device not freed. I'm just looking at the errors that we had before. I'm assuming right now it's doing self-test diagnostics. Let's see. That one was a bit anticlimactic because the computer is working and we weren't seeing the serial output, even though we should have been. The tape drive keeps doing stuff over there. Oh, I was away because I thought it had frozen. Warning, config info invalid. Primary boot, but I see I'm pushing stuff on the keyboard and It is not doing anything. I don't think my transmit line is getting through properly. But check it out, 2 megs of RAM, self-test complete, Plexus primary boot revision 1.2, boot disk, SCSI device not free. Okay, I guess that's fine. Now, if we look at the serial settings, I do not have any flow control turned on right now. That means that it's not looking for like a signal before it can transmit any characters. And the fact is, I'm pushing enter, pushing, all sorts of letters on the keyboard here, and absolutely nothing is happening. I'm pushing Control M. That wasn't me. That's just it exiting the boot process. Obviously, it's trying to find some kind of a hard drive. And since the hard drive is not actually connected to this, I assume it's trying to boot there. I don't know. But I should be able to type commands. I'm pretty sure that that's a prompt, and we should be able to do stuff. And the fact is, it's not working. I have to say I'm extremely relieved that it is not boot looping anymore. This is excellent. I mean, I was completely worried that this thing was going to be a nightmare to troubleshoot, because the board, by the way, when I was looking at it, it's a multi-layer board. I can see there's traces underneath the top layers, and that just makes actually troubleshooting boards when you don't have schematics so difficult, because traces are underneath other things, and it's a bit of a nightmare. So the fact that it's passing its self-test diagnostics is freaking excellent. I think to troubleshoot this problem, I'm going to clip onto the MC1489. I think that's the chip that is receiving the signals. I'm going to hook the scope up to it, and we'll try to send a text file through PuTTY here, because that's the problem is I can't, I have a wireless keyboard. I can just take it over there and type. I was thinking like, I can't type in the terminal from over there, but yeah, wireless keyboard. Okay, so I'll take the keyboard over there and I'll send some letters and I'll look at the oscilloscope. That is the right thing to do. All right, so the system is booting up. There are the LEDs here. I power cycled it and they're not flashing, so that's a good thing. But I noticed when I turn this on, it does go through several of those flashes, kind of giving me flashbacks to earlier in this video, so a bit scary. And you can see here we're getting the P, 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 P. It's sort of doing the same thing. It falls out of it though, and then it starts to work. Although you can see up here, I powered it on earlier, and we got multi-bus failed. And now it's just sitting here doing nothing. And it's been quite a bit longer than it was up here where it actually worked. So I'm not completely convinced that this thing is actually working properly. I mean, at least we're not getting the continual reboots. At least it does it for a little bit and then it stops. So that's good, I guess. For troubleshooting the serial console, I actually have a clip on the MC1489. And the input for the transmit line that does come from my lab computer, it comes in on pin 4. And according to the data sheet, it's pin 6 that is the output, the TTL output, that makes its way back to the MOSTEC SIO chip here. And this is actually the slightly troubling thing. On the scope, if I type on the keyboard, we are getting letters. So pushing random keys on the keyboard, and you can see there it is, hitting enter. There is, I guess, the enter key for serial. Oh, okay, and that noise that it just made is actually the diagnostic completing. So it actually worked, no error. I don't know what that multibus error was. It might have been because I didn't turn the system off for long enough. So it's working, but I push all the keys on the keyboard and the system does not respond at all, which is annoying because I know that that transceiver is turning the serial RS-232 into a normal TTL signal, which we see on the scope there. So why doesn't it register any key pushes? Yeah, why indeed? I was just pushing J on the keyboard and there's a bunch of J's typed on there. Yeah, that is me typing and it is freaking working all of a sudden. What the heck is going on with this thing? I hit the backspace key and it says rub out encountered, error number 127. Right, I am capturing the desktop now so you don't have to look at me recording the screen anymore. So this is a test. I am able to type. Looks like, oh yeah, caps lock, it has lowercase support. Let's try some commands. Help. And that just froze. This is where having the manual would come in so handy. Looks like it tried to load something off the SCSI device. Okay, Question mark? Oh no, nothing's gonna work. So last night I was doing a little searching and I found this document here, Plexus System 3 Unix 3.1. The date's a little bit earlier, so I assume as opposed to Unix System 5 Release 2, this is a slightly earlier version. There's a little bit about reloading this operating system, and it does confirm, at least on this particular Plexus, which I think is for the P40, that it does use the tape to actually do the loading. It mentions here that you can run a command called dconfig, which checks block 0 on the disk. And there was one of my patrons who theorized that block 0 is actually where it stores the disk parameters. That was the stuff I talked about in the last part, where the SCSI controller or the interposer needs to be set up with the disk parameters. Well, it's actually stored on block 0, and when the system boots, the ROM will load that parameter table off the sector 0 and then configure the SCSI controller. I'm assuming dconfig is not a command we can run, and yeah, it doesn't look like it is. So this must be a command you run inside the running operating system itself. Actually, look, it does say, shut down your system, press reset, obtain the primary boot prompt, which is obviously what we're at now, then run the standalone dconfig. If you need to get the dconfig program off tape, you will have to mount the tape. So I guess that's something that does need to load either off the disk or a tape, and we don't have either right now. Anyhow, this is what I was reading last night. Turn on the system, press the reset button. Wait for Plexus self-test revision x.x to complete. The system informs you about the disk and tape driver names in use on your system. Well, it's not telling us anything right now, e.g. PD or PT, primary disk or primary tape. It tells you about the various boards, Ethernet, ICPs, and tells you about the memory size. The boot message is Plexus primary boot revision 2.0, and we're getting Plexus primary boot revision 1.2. And after the boot message, you get the : prompt, which is the boot prompt. The disks come pre-formatted from the factory. In the event of a major catastrophe, you'll be required to format the disk. See the user manual for instructions on how to do it if necessary. Make a system file on the disk with the mkfs command. Let's just see if these even work. I mean, I assume it's trying to load this off tape, which doesn't exist, right? To do this, mount the release tape and respond as indicated in bold. So yeah, it's trying to do something like load off the tape, which doesn't exist. The sequence is mkfs, and you do this, and that obviously creates or formats the file system on the new disk. And then you use this restore command, which will actually restore the operating system off of tape, I guess. And then for system startup, obtain a primary boot message with the : by pressing reset if necessary. Once you have the boot prompt, type return. The machine should respond : sys3, and the following will appear. And that's it, obviously loading the system into single user mode, I might add. I was concerned in that first part we didn't necessarily have the root password, but we do. And the fact is, if you boot in a single user, it doesn't matter anyways, because you could just use the password command to change the root password. It says you're in single user mode, so to go to multi-user mode, you just do init2. Yeah, it's the old school init commands. And then you run the multi-user, type Control-D, and you'll get the login prompt. So this is actually useful info. I don't know how appropriate it is for this particular machine, but it still is useful. Now it's just talking about doing a system update. This is all stuff inside of Unix itself, which of course we don't have working yet. Further down this document, it actually has a little info on LEDs, and on the front, it does have a 0 through 7. I just assume those had to do with the serial ports, but I guess not. On this machine, LED 7 is green and the rest are amber. If I turn out the light there, hopefully you can get an idea of what the LEDs are looking like right now. So 7, which is the green one, is lit and it says waiting for disk. Also 0, 2, 3, and 4 are all lit. So 0, 2 doesn't mean anything. It says they're reserved, at least on this. 3 is swap in progress and toggle for 1 second for 4. Okay, I don't know if those really make sense on this particular system. Unfortunately, at the end of this document, there wasn't really anything more about this boot process. So I wonder what some of the commands are that we can run in here. Nice thing is, the system is still working, it hasn't rebooted, and I can still type commands. Incidentally, hitting backspace gives us this rub out error, but if I type hello and I hit Control-H, that does allow us to, retype what you needed. You can quickly fix that in PuTTY here by just changing this to Control-H. Some of these commands actually seem to do something. So hello and Adrian, those just give an error right away, but help actually pauses here. So my assumption is if the tape were in there, it would be trying to run a program here that to actually give us some help. I'm gonna type /sys5 just to try, and that's attempting to do something. Part of me wonders, if we try to decompile the boot ROM, is that going to give us a list of all the commands that we could actually run inside of here that don't require loading off of the tape or disk? I'm just noticing that when I type, the LEDs blink on the front of the computer. I think it's just literally printing 4 bits from whichever character you're sending. It's sort of like a little bit of a diagnostic, I guess. So if I send the character 1, I just have the bit 1 lit up. 2 is binary 2, 3, you know, and so on. And the same for different letters, pushing letters on the keyboard. It probably just shows the most significant bits or the least significant bits or whatever. If someone knows ASCII off the top of their head, it's probably what's happening there. I think what I want to try here is I want to turn off the machine, and then I'm going to turn it back on, and I just want to make sure that we could still issue commands to it. Now in that documentation, it was kind of interesting how it talked about turning on the computer and pushing reset. I wonder if that is necessary for like the initial startup of this machine. And maybe what you're supposed to do is turn the key all the way to the reset position when you power on the machine, and then put it back in the run position, and then it will boot normally. Let's give that a try. All right, so the machine is off. And now let's turn it on and put it to the reset position and let it stabilize, the power supply that is. And then we turn this to the run position. I think that might be it. We did not have that repeating Plexus pattern. It just went right to self-test. So maybe you need to wait for the power supply to stabilize. Otherwise you get that constant rebooting. Oh, that reminds me, by the way, I looked everywhere on the motherboard for a 555 or a 556 timer, which is typically used on most systems in the 80s for the initial reset circuit. And I did not find it anywhere on there. But when I was changing out the fan, there was a 556 inside the power supply. So that might be something to do with the reset. Oh no, multibus failed. There's that error again. I don't even have the whole card cage even in there. Not that the card cage does anything. That is interesting. I wonder if I need to turn the machine off and let it sit there and wait for a little while. And I also wonder, is it still booting? Oh, okay, no, it's still, oh, self-test failed, okay. Config info invalid, So right now 0 and 3 are blinking, which I assume is the failed message for the self-test. I'm gonna turn the thing off and let it sit for longer in an off state. Part of me has me wondering if the battery backed up RAM, which is also the clock chip, same as a PC, is corrupted. Kind of like what happens on a PC when you first boot it up. You know, you have to initialize the default values. And it seems like you have to do that once the system is booted with that deconfig command. Or at least that seems like what you have to do according to that paper we were reading. So maybe what's happening here is it like thinks it has multi-bus, even though it's not configured. Yeah, I'm not really too sure. So maybe just leaving this off for a minute and let me try turning it on. And I'm gonna do that reset trick where I put it on reset first, let it stabilize, and then see if it boots. No, that looked like it rebooted a couple times, and I see we got Plexus 3 times. So we're not totally out of the woods when it comes to that weird rebooting that's going on. At least it seems a whole lot more stable than it was last night though, before I changed that fan. Oh no! Now it's saying that the main board has failed. I'm gonna fiddle around with this thing a little bit, just see if I can figure out the weird idiosyncrasies of this process. Okay, look at that, self-test complete. So what I did is just turned it off, waited like 30 seconds, turned it on with the screwdriver here. I went immediately just right to reset, just straight to reset, let it sit there for maybe 10 seconds, switched it back to run, system booted up normally. I didn't get any of that rebooting going on. And can I type? Hello, yes, we can still type. Excellent. So clearly the next logical thing for us to do is hook up the original hard drive or maybe the MFM emulator hooked up to the SCSI interposer and try to actually boot Unix. So I went ahead and reinstalled the hard drive into the chassis. As a reminder, this Fujitsu hard drive is MFM or ST506 interface, but it is actually connected through these cables to a SCSI interposer that is mounted inside this computer between the power supply and the motherboard. And on the motherboard side, this is a 50-pin SCSI connection which goes to that interposer board, which does the translation between MFM and the SCSI interface that this motherboard uses. The floppy drive on this computer, which is a Sugart double-sided double-density 80-track drive, so about 720K, is also connected to that same SCSI interposer, so that essentially this is a SCSI floppy drive, even though this is a standard PC floppy drive. So if this drive doesn't work properly, I can swap it out with any standard PC floppy drive. I have a few things that I'm worried about when it comes to powering this on. We know the hard drive is working. I think the SCSI interposer works, although there's no real way to test that. I think the bigger problem is that the motherboard lost its configuration settings because the battery that was on there died a long time ago. And I am concerned that the drive parameters, the heads and cylinders and whatnot, is stored inside that config variables in the battery backed up RAM. And since it's lost, I just don't know if the system is going to be able to read those off this hard drive once it spins up and configure those, because the interposer does require those configurations set. Now in the boot ROM, you can run some commands, but unfortunately they don't seem to be embedded into the boot ROM. They seem to want to load from the disk itself or potentially from the tape drive. Now the operating system for this machine seems to be distributed on a tape. So if you have a hard drive crash and you need to reinstall your OS from scratch, you use the tape drive to format the new hard drive, make a new file system, and then restore it all back onto the drive. We of course don't have the operating system tape, so there's no way for me to run any of those commands unless they're able to be loaded off the disk. When we turn on this computer, if it's not able to configure the drive based on like the first sector on this disk, which it should be able to access, and it's looking for us to run commands off tape, we're unfortunately going to be dead in the water. So with all that said, it's now time to actually hook this thing back up to my lab machine and power, and hopefully we can get this thing working again. All right, I'm all set up with the capture. Putty is up, everything is ready to go. I got my screwdriver ready, and it's like an old stolen car here. I'm going to turn this to the reset position. I'm going to let this all spin up for a second. The hard drive is spinning up. That's a good sign, right? All right, that's long enough. I'm going to turn this to the run position. There we go. It didn't do any kind of boot looping. Oh yeah, we got one Plexus, that's good. There we go, it's going to run the diagnostics. Let's hope that it doesn't do any fails. We were getting multi-bus failures yesterday, and we got one mainboard failure, but then generally it was working okay. Okay, self-test complete. Oh, it sees the hard drive. SC0 and SC7, I guess one is the tape drive, or no, oh, I don't know actually. SC0, I don't know if that's the hard drive, and SC7, that just might be the interposer. But the thing is, the tape drive is connected, and that's a SCSI device as well, and I think that should show up as some kind of SCSI device. Now I know I'm not typing anything here, I'm just waiting, but I don't think it's ready. Oh, I hit enter, and it says /Unix. Oh, I think it's doing something. The hard drive LED is flashing on there. You gotta be kidding me. No way. I know you can't see the hard drive LED. It's sort of blocked behind the case itself. But, system 5.2 R8, single user mode. I was so concerned about the root password when that was not actually anything to worry about. Oh wait, no. It's gone to run level 2, which is not single user mode. Is the date correct? It is not correct. Oh, this is amazing. Date format, mod Y HRMN, and then brackets year. What? I think what it's asking for is month, day, hour, minute, and then year, optionally at the end. So we have 5/23. Time is 1707, and then the year, I guess, yeah, okay, so it has an example right here, I just noticed that. So the year is 2 digits at the end. So the year is 24. Is it gonna take this date? It did not take the year correctly. It thinks it's 1970, so I'm gonna say no, and we're gonna type this again. I'm just gonna paste in their example here. This might not be Y2K compatible. Oh yeah, so that is how it works. 86 was the year. There we go, I put in May 23rd, which shows up as Thursday, 1996. So that is close enough. I can't believe this thing is working. Do you want to check the file system? Sure, let's check the file system. Oh, wow. Okay, so couple things. It looks like it absolutely loaded the parameters for the hard drive off sector 0. Some of my patrons theorized that's exactly what would happen, and it is what happened. Oh, that is so cool. You can see the blinky blinky lights as well. They're doing stuff. That is freaking awesome. I am absolutely flabbergasted that this thing just freaking works. I mean, obviously I had to do a little bit of work there. I was trying to be super careful the whole time with this system. I wanted to make sure I preserved the data on the hard drive. So let's look at what's happening here. So far, nothing looks out of the ordinary. So we have what looks like two partitions, right? Root volume and /user volume. Warning, mounting /user as user. Move cannot access something or other. Oh, that's kind of weird. Initializing RKER. Arker. What's Arker? Moving on. LP scheduler. Unix system 5.2. Copyright 1986. So this obviously has a little bit of an update. Okay, console login. So we got root. When I recovered the OS off this drive, I knew that the root password might be a problem if we ever got this computer booted. So what I did is I looked for the password files in the binary dump of the hard drive, and I was able to extract what you see here on the screen, which is different hashed passwords that look like from various password files that were all over this machine. So I went over to Patreon and I asked my patrons if someone could reverse the password so that when this situation happened, I will be able to log in. And in no time flat, my patron Hein came back with the answers. And it seems that the password that was being used on this system for the root account is just half pint or blank. It might be blank or half pint. So I think the first thing we can do here is let's just try out root. Oh, I put an extra slash there. That's not going to work. It did work. I don't know. I accidentally typed the backslash and then I just hit enter for blank and you gotta be kidding me. What? Let's try that again. So root, and we hit enter for blank. Oh, and that works. There's no password. So all that work wasn't even necessary. Let's try that here account. Let's see if that is a real account. And we'll put half pint as the password. That works as well. So, and it put us, that is so cool. Yeah, there we are. We were in the root directory. So let's just take a look at what is the actual password file on this machine. Oh, wow. It's a bunch of accounts. So if we compare this, well, the interesting thing is looking at what I extracted doesn't seem to match what's actually here. We have RVXY, and that seems to be on this /dev root, but unless I'm missing it, I don't see it on any of the other root accounts here. So there are a few other accounts in here. There's one here called off. We also have what are obviously the users on this particular system: Woody, Work, Ed, Lack, Guest, Jan, Colleen, Bob, and Jim. Hi to any of you if you're watching this video. Now this machine obviously belonged to a company. There would be no reason why like a home user would ever have had this computer. So I don't want to show any like personal information or any company information that's on here, just to protect the people that were originally using this machine. So there might be a little bit of blurring that has to go on the console output of this machine. So let's poke around the system a little bit. I've never used anything as old as this. So these are the processes, I think these are all of them that are running right now. You can see here we're running the PS command from the console, and we have TTY1 and TTY2, and it's running Getty. So that means that there should be at least 2 more console ports active on the back of this thing. Now it looks like we're running shell, but I think C shell is actually installed on this. Yeah, okay, we have C shell as well. I'm not super familiar with C shell. I know bash, of course, because that's what's used on Linux these days. So I'm curious, we saw in like that instruction manual that we would have to run the dconfig command, but that doesn't appear to be anything we can run. I popped over to user bin just to see what's in here. There's a whole bunch of stuff that starts with a Q. Qcrypt and Qconvert and Qdraw. And one of them here is Qoffice. And I'm wondering if this is like some kind of an office suite that's on here. What I don't find immediately is that dconfig command to set up the configuration of the machine. In case anyone is curious, uname reports sys 5.2, Unix 1.2, R8, M68. We have a /user directory, and in here appears to be stuff related to the user account. And yes, it seems like /user is the equivalent of /home on a more modern Linux distribution. There's a help program here, help stuck. If you know the value of a system error, you can look up the description in intro 2. If you don't know the error number, you don't understand what's going on, try the following. Make sure the answer isn't in the documentation. Well, we don't have that. Try to write to anyone logged in as ADM. So I guess this is like you could write to all kind of thing. Step 3, contact your Unix counselor. And step 4, File and MR. See the system administrator for instructions. What's MR? You know, I think that intro 2 is a man page, but if I type man intro, we don't get anything. It's just telling us bad directory for catman. Yeah, there's no catman directory here. But there's a doc directory. Yeah, we have a few things in here. All right, so the README says, this letter is designed to highlight the new features of Q1 and QOffice. Operational descriptions of each feature are contained in the July update of QOffice. Q1 has multi-column text, graphics space reservation, index generator. Yeah, integrated menu system, new features. Okay, so it's some kind of office suite. I wouldn't be surprised if this QOffice is the only thing that's actually on here. All right, I just wanted to see if there's a C compiler on here. Let's see, is the which command on here? No, that's not there. So CC obviously would be a C compiler, and it does seem to be on here. And yep, there's a linker as well. So that means that we could probably port some stuff to this machine. All right, so this is weird. We have a directory here, 2020, which I went into. What's the deal with this? 2017? Was someone using this in 2017? I noticed when we looked at the user directory, /user, where I had the user accounts, those had date stamps around 1989. But 2017, that's kind of unusual. So the file in here called releases.txt, technical notes for 2020 on the Plexus P35. This looks like it's some kind of a graphic thing for plotters or terminals that support graphics like the VT420. We have a directory in here called tutor, and inside of here are just a bunch of files, and they all have 2017 date stamps. I need to find a log file. There's got to be logs on here somewhere, and we can try to see if this thing really did boot up in 2017. You know, unfortunately, the find command returned absolutely nothing. So unless I have the syntax wrong, let's try that again, but I will look for those TMF files just to make sure that it's actually finding them. All right, obviously my syntax is wrong because it didn't find the TMF files. I think what I'm gonna do now is stop the recording, and I'm gonna start poking around the hard drive and take some notes, try to figure out what I can figure on this machine, see if I can find some log files or any other evidence of when this machine was actually last used. I also wanna try to get the floppy drive working, because if we're gonna try to get files off and on this machine, that might be one of the best ways. It doesn't look like Kermit or Z-Modem or any like file transfer utilities are on this thing. So that's another way we could transfer files is over the serial connection. So I'm gonna do some more poking around and see what I can figure out, and then we'll be back. Well, unfortunately, that went down the drain very quickly. You can see behind me, the machine is sitting there. I actually put the lid back on it because I wanted to make sure the computer was getting good cooling. So with the main fan hooked up, the motherboard was gonna get lots of air around it. I actually did that because while I was poking around on the hard drive trying to look for interesting stuff, the computer crashed. I was about to show you the crash messages, but might as well show you the things that I found poking around on the hard drive. So inside the etc directory, there was this config file that talked about the various serial ports on the back. So first thing it does is set up the console on serial 0, which is the one I was connected to, and then it goes ahead and runs Getty on all the other serial ports, so 1 through 7. Oddly enough, 4 is set to 1200 baud. Don't really know why. The rest are 9600. Continuing to poke around, I found /user/ADM, and this was some logs and stuff. Unfortunately, most of these files just have 0 bytes to them, and even the ones that have like 68 bytes in them really didn't have anything in them at all, except for just a header. And the only file that had anything, well, that was actually in there was SUlog. But inside that, all you really got was this. If we scroll down, we can see like Janet-root. I don't know what that exactly means here. Ed, yeah, I think that's one of the usernames, right? Ed. But unfortunately, there's no years on any of this. Now, the timestamp, you know, I didn't save the timestamp, but it was like 1989, I think. And unfortunately, that was it for log files. Now, there was a games directory as well, and inside of here was a bunch of games that probably all come with AT&T Unix System 5 Release 2. One of them was called Robots, and it looks like we have various users playing stuff. Now, Woody is one of the usernames on this machine, and there's a lib directory right here, and that contained the high score file. And the high score file did also have a date of, I think, 1989 or 88 or something like that. So it shows that people were actually playing games. Now, when I was poking around some more on the hard drive, I went to the include directory, I typed S, and it says command not found, and then the computer crashed. We got this remote kernel bus error, like some register stuff. The remote kernel just says halted, and it ended up at this prompt here with a plus. And I could type stuff, but I didn't know what to do. I like tried a few different things and nothing seemed to work. So I put the computer in the reset mode without powering it off, let it sit there for a while, and then put it back to run. The computer booted up and was working okay, and then I was just looking in a directory, and the same thing happened. It crashed and it halted. And this time it didn't even give me the plus prompt, so I couldn't even do anything. So I turned the computer fully off, turned it back on with doing the reset first, then tried to boot up. And unfortunately, it passed diagnostics and everything was fine. Then I hit enter to start booting Unix, and then it started, and right away it gave this SCSI error type 1. And that brings us to where we are right now. You can see there's that SCSI error type 1. And now every single time I turn the machine off and on, or even just try to soft boot it, I always get self-test failed from the main board and this code 4F02. So I tried rebooting a few times, which is why you see it over and over again. It doesn't just try automatically. I power cycled the machine. And then what I did is I turned the computer off, and then I went and got dinner. So I let this thing kind of fully cool down for a while. And unfortunately, this most recent one right here, it was just right now, I just turned it back on, and it starts running the self-test and immediately fails. So there is clearly some kind of hardware problem on this board, and that's really scary to me. I was actually really excited to finally get to try to play with this computer a little bit, and I was going to try to load some software onto here. I was going to find the source code for something like Kermit and copy it over like text mode onto that machine, try to compile it, and then I was going to try to put a few more tarballs over there with source code for various tools and stuff, and see if they could be compiled and, you know, that kind of stuff. And yeah, the machine is just dead now. It does not work at all. So I'm not ready to throw in the towel yet. Let's open up the computer and start poking around in there and see if I can bring some life back into this thing. I'm hoping it's just a dodgy connection on a socket maybe. I don't know. I'm not quite sure what could be causing this. Well, the motherboard is back on the bench. And unfortunately, it's degraded even worse than it was just a moment ago, where it was failing the diagnostics. Now it doesn't even start. Now, I took a look at the reset pin here on the power connector. Remember I said this was the one that comes from the power supply? And very briefly, when I was fiddling with it in the computer, it actually started doing that boot loop thing again. And sure enough, that particular pin that I think comes from the power supply was going up and down, up and down, up and down between 5 volts and 0. Now what I haven't figured out is, does that reset signal on that pin come out of the motherboard and go into the power supply, or does it come out of the power supply and into the motherboard? I'm not totally sure. And I took a look at where this goes on the motherboard, just tried to trace that out. And it goes to the reset pin right here on the clock/CMOS whatever chip. But it also makes its way over to this MC1489, kind of similar to the serial ports, and it makes its way over to these resistors and these transistors here. So what could be happening is the reset signal comes out of the power supply, affects the clock chip here, and then goes into these, and these are like buffers that drive the signal all around the different parts of the motherboard for like different types of chips. Some chips are going to need reset low, and some are going to need reset high, and maybe that's what it's doing there. It's converting it into those two types of signals. Why aren't they using TTL logic there? I'm not totally sure. It's very difficult to trace all this because there's a bunch of traces that are underneath the layers. This board, I think, has 6 layers. Has the traces on the top, the traces on the bottom, then there's another set of traces on the top and the bottom, and then there's a ground plane and a power plane. I can tell there's both a ground and a power plane because when you look at the 5 volts and the ground on the power connector here, there are no traces coming off any of those pins, so they must be connected to internal planes. So a 6-layer PCB is really difficult to troubleshoot just because you can't see what's going on. I guess I should check to see if these are shorted, these transistors here. I think this has something to do with the reset circuit. Now the bad thing here is there appears to be multiple problems happening at the same time. This reset circuit thing, I think is related to what we saw in part 2, where the computer was boot looping. But the failed diagnostics, I think, is a completely unrelated problem. And even if I fix this reset issue, I think we're still gonna get stuck with the failed diagnostics. All right, so checking these transistors, none of them are shorted. So the problem's not coming from that. I really feel that it's the pin 4 coming from the power supply. That circuit in the power supply is messed up. So maybe what I just need to do is just try to override that, and I'll just drive this to 5 volts, because it definitely seems like when this is held down at ground, that's when the computer just stays permanently in reset. I think what I'm gonna do is I'm going to cut the trace for the reset signal that comes off the power supply pin, and then I'll add a bodge wire that goes from the pin on the clock chip, and I'm going to have it hang over the top of the motherboard. That way I can ground it or pull it to 5 volts relatively easily. So I'm just going to cut the trace right here, and it'll be easy to fix if I want to restore the motherboard back. Just put a bodge wire. Okay, that is not connected any longer. I guess while I have this out though, I'm just going to lift these chips, not the EPROMs, I already took those out, but the CPUs and these various PAL chips. I'm going to pull these out of the board, and I'll maybe put a little Deoxit in there, and then I'll pop them back in. So if the reset problem can get fixed, and then the thing passes diagnostics by some kind of magic, then that would be awesome. Otherwise, I think we're up a creek. I'm just going to start over here and go methodically through all the chips. It was really nice that Plexus put all the PAL chips in sockets, and they used very high quality sockets as well. This whole computer is extremely well built and really easy to service, frankly. All but 2 of the PAL chips had the original labels on them, so when you see a sticker on a chip, you know that that's a PAL chip. Now, we know of the architecture of this machine. One of the CPUs is used for I/O, and the other one is used for jobs, which I think is the actual OS running. It seems the reset lines of these 2 CPUs is not connected together. That's what I was just testing with the multimeter. This is almost certainly because the computer boots up on one CPU and then loads code into, say, static RAM, and then starts executing the other CPU, so it releases the reset on that one later. While going through all the sockets and checking them, there was absolutely no corrosion or any pins that were bent or anything that was out of the ordinary. Everything looked completely perfect. Now on the back side of the board, I decided to take off the RAM card, inspect it, plug it back in just to make sure that maybe there wasn't a dodgy connection there, but no, everything looked just fine as well. All right, the motherboard is back in, and I have a bunch of stuff clipped on here. So what we have on the oscilloscope is 2 different probes. This one here, which is the yellow trace, is actually coming from the power supply. It's on that pin 4, the one that I cut. I forgot to hook a bodge wire up to the back, so what I did is I clipped onto the reset pin that's on the clock chip here, and that's what goes over here to these transistors and everything like that. That is the blue trace right here. Now what's funny is the power supply is currently connected to the back here, and the reset signal doesn't stay right around ground. It actually comes up to about, I'm going to say that's about 0.8 volts. If we unplug the power supply, you can see there it dropped down. All right, I plugged it back in, it went back up. I think the reset circuit in the power supply is just bad. Something's wrong with it. So with things like this, if I turn on the computer, what's going to happen is, well, that reset line coming from the power supply is just noisy, but it doesn't, I mean, it's not doing anything. And then the reset line that's on the clock chip, the blue trace, is just stuck down at ground. So that means the computer's stuck in reset right now and it's not operating. And I think you can kind of tell that there's 2 LEDs lit, LED 0 and LED 8, which is kind of how it just works when you first turn this on, when the computer is stuck in reset. Now I have an 800 ohm resistor between these 2 clip leads, and it's on 5 volts on the power supply connector. So this end right here is 5 volts through 800 ohms. If I clip it onto the clip here that goes into the clock chip, that's the reset line, then theoretically the computer should come out of reset. So the blue trace should go up. Okay, it did, see, boop, right there. And right away the green light's on, and we got blinking lights on the front. And now number 2 is blinking. And by number 2 blinking, I am pretty sure that is exactly the same fault we had before we started, excluding the reset issues. This is that main board self-test failure results in this. And sure enough, there's the diagnostic error. I cleared the console, so we had a fresh start. Self-test failed, 4F02, same freaking error. I'm gonna turn this off because it's kind of noisy. So what did we figure out so far? Well, we figured out that the reset circuit is definitely handled by the power supply itself, and there's something wrong with the circuit inside the power supply. So I just bypassed it by doing this whole resistor thing, and theoretically, with a 555 timer, we could just replace the entire power supply reset circuit and maybe even hook it up to the switch on the front so you still have access to reset the whole system and just not rely on the bad circuit in the power supply. Now the problem is clearly we still have a fault on the motherboard, and I unfortunately have no idea what it is. Incidentally, before I took the motherboard out, I didn't show this on camera, I unplugged this SCSI cable. It's plugged in right now, but I had it unplugged, so it was just the motherboard on its own, and it was still failing that self-test in exactly the same way. And I also went and double checked that the voltage rails still look good, and all of them do, -12, +12, and 5 volts, nice and clean, no issues whatsoever. So I don't think we're having a power problem right now. We have a fault that has developed on this motherboard. Now, it's quite possible the original documentation for the motherboard, the error code that we're seeing with the diagnostic might have like a pointer to what might be the problem. And that could give us a general idea of like where to look on the motherboard. Although without schematics, I mean, I can't really make heads or tails of anything on this motherboard. Now, even if we had an idea of what was wrong with this board, like say SCSI controller failure, there's nothing on the board that indicates that, hey, this is the SCSI controller. On a Macintosh, there's a SCSI chip. So you could just look to that and the logic that controls it. But on this board, the SCSI must be communicated with directly from the CPU. I guess that I/O processor, one of its functions is to communicate with SCSI. So it just has a bunch of TTL logic and PALs, I guess, that handle that. It's not done with an actual controller chip. The only controller chips there are the 4 serial ports back there, but those seem to be working well, at least the one that's displaying the console, and I just don't think it's necessarily related to that. Now, it's possible maybe we have a bad CPU, like one that's failing. I guess I could swap the 2 chips around and see if that makes a difference. I did make copies of the ROMs, so I could make a fresh set of ROMs and put them in there. Maybe one of those ROM chips went bad, and that's simply a ROM checksum error. Although, now I think about it, I think when we were looking inside those ROMs in part 1, there was a ROM checksum or some checksum error messages that were in there. So you figure if it's booting up with a checksum error, it would have just said that. And if we think about the symptoms of what this thing had when the OS was running, I got bus errors, so it was crashing. And I don't think that's necessarily a RAM problem. I mean, that's just some kind of a logic problem on the motherboard. So maybe before I throw in the towel, let me try swapping the CPUs around, see if that makes any difference whatsoever. Because if one of them is slightly bad, then the error should be different, or it won't boot at all, or whatever. We should see a change. And then I can make a new set of ROMs. I'm pretty sure I have 27, 128 handy. So I'll make a new set of ROMs. I'll swap those out. And then after that, I'm not sure what else to do. I guess I could like take all the RAM off and start testing that, but I don't know if that's the problem, because I recall in the diagnostic ROMs, when you look at them, there's definitely stuff that looks like RAM error. Although maybe not. Maybe this is just simply a RAM problem. So let me start doing some poking around with the CPUs and the ROMs on this side of the board, and we'll see if that makes any difference. Okay, I've done lots of stuff. So this is the RAM card, and I tested every single RAM chip. I went ahead and I used the DRAM tester that I had here that a viewer sent in. Thank you very much for that. And I tested every chip, and not a single RAM chip tested bad. I put a little mark on every single one that tested good, and they all did. In case anyone wants to see the RAM card on this thing, there it is. It's pretty typical stuff, just TTL logic and a whole bunch of DRAM. This is 2 megabytes of DRAM, and it all tested absolutely perfect. With the motherboard here, you might be noticing something here in this upper area. Well, I decided to use the Dremel to clear away the solder resist from the top of those traces, because remember that was the battery damage area, and I just wanted to make sure that there was nothing broken. It can be really difficult sometimes to see if there's a via that connects to a trace, if that actually is broken. And so I cleared it all off, and I verified that every single via and trace has good continuity, and unfortunately it does. There was no issues up here whatsoever. That's not to say there's not a break inside the PCB, maybe like on a lower layer that I can't see. That is totally possible. But at least on this top side, no issues. Before I took drastic measures and tested all this RAM, which incidentally took a very, very long time, I did do some stuff on the board here. So I also checked that all 4 of the ROMs match. I didn't make new ones. I just took these out and I put them in my programmer here, and I verified that what I had already dumped when I first started this matched what's in these, and it does. It definitely does. I also took the CPUs out and swapped them around, and that didn't make any difference. I did figure out that the top CPU, though, is the one that runs the self-test. Without this one, you don't get any activity on the system at all. With the bottom one removed, doesn't seem to make a difference. I'm still getting that same exact failure message, and that happens whether this CPU is in there or not. I don't think it's even getting to that stage of the test. It's failing before it even gets to the second CPU, but this is the one that is running the diagnostics. There are some jumpers spread around this board, including these 2 right here. So just for fun, while this was installed in the system, I moved these over to a different position just to see what that would do. And that actually had an interesting effect, but not a positive one. You can see the diagnostics are failing here, main, 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 and then we got SIO and a different code. And that happened when I moved those jumpers. And this happened even more quickly than the failure that says main with T4. I'm pretty sure that T3 and T4 means test 3 and test 4. And the reason why I say that is if we bring up the ROM here and we take a look at these diagnostics here, I think these are the tests in order. Test 1, test 2, test 3, that's the SIO failure, test 4, main, and then job, which I think is maybe the second processor, I guess, I don't know, map, which is the memory map, I think, or maybe mapper is, I don't know what the difference is here, then SCSI, then multibus, and we saw those failures previously, right, or at least the multibus one, when I was trying to troubleshoot those rebooting issues this thing was having. Then clock, register, priv or private, parity, bus, prox, and no test, whatever that is. I'm noticing that none of these say RAM, but parity clearly has to do with the parity memory. Static has to do probably with the static memory that's on the board here. There's a bunch of static RAM. That probably tests in that section. And then bus must be like maybe a shared bus between the two CPUs or something like that. Prox, maybe the two processors to make sure they're running properly, I don't know. And then self-test complete. So at this point, I have found absolutely nothing wrong with this board. At least nothing that I can see is wrong. Now I have handled the board and I've obviously tested and reseated all the memory here. So what I need to do is put the memory card on this, put this back in the computer, and just verify that we're still stuck at exactly the same spot. And then we'll see what happens. Motherboard is back in. I haven't turned it on yet. I am ready to bring the reset line to high once the power stabilizes. And I cleared the scrollback buffer, so we'll see Plexus if it boots up properly, and then we should see, well, the error or it actually working. Now, the SCSI cable is disconnected from the motherboard. It's just the power cable. All of the other peripherals in the case are totally disconnected, by the way. Hard drive, interposer, tape drive, floppy drive, everything else is unplugged. It is literally just the power supply and the motherboard. So let's see what happens. Okay, system is on. I know you can't see me here. And I'm gonna clip the reset line on. Okay, there we go. It says Plexus. So at least I didn't break the thing. Oh, there we go. Same exact freaking error. So disappointing. That's so unbelievably disappointing.
On that disappointment, I took a break for the evening. Let's regroup in the morning.
So where we left off, there were two major faults in this system. The first was the power supply, which is connected to the motherboard here, and it's behind the motherboard. It actually has the reset circuit for the motherboard in it. What happened when the power supply reset circuit failed is that it was constantly leaving the computer in a state of reset. It never brought it out of reset, which is bringing that pin there for up to 5 volts. And then the other big fault with this computer is an actual showstopper where the system fails its diagnostics and goes into a halt state. That gives us an error code, which I still don't quite know what it means, but if we're going to try to investigate any of that stuff, I need to first sort out this reset problem that's happening here with the power supply. Now, it goes without saying that I can obviously just open up the power supply and, well, try to figure out the reset circuit that's in there, and that should get that circuit fixed. But I have to say, when I was in the power supply multiple times, I noticed that there were several ICs inside there that obviously make up some voltage comparators. There's some overcurrent protection stuff and some other things that I think all lead to the reset circuit essentially keeping this motherboard in reset to, I don't know, try to protect it, or so you know there's some kind of fault. The power supply also does shut down, because I did see that. I noticed the 5 volts from the power supply would just disappear altogether, which was obviously that voltage protection stuff happening, probably because some voltage was going out of spec because of the excessive ripple. Now, it goes without saying that opening the power supply and trying to troubleshoot that thing is probably the right thing to do, but is it the thing I'm going to do right now? No, it's not. I want to get away from using the whole resistor stuff that I was doing in part 3, and I'm going to make something new that's just going to drive the reset circuit on the motherboard and do it in a way that I can control it, so I'm not relying on a faulty power supply circuit to do it, and then we have better control of the system. I talked to my friend Frank about coming up with a new reset circuit, and he actually recommended that the reset circuit in the original PET 2001 is a very solid circuit. It uses a 555 timer and a few little components around there, and this would actually be a really good way to implement a reset circuit that would work on this machine. And in fact, when I was inside the power supply, I did notice that there was a 556 timer IC in there that is obviously part of the reset circuit. So to replace it with something like a 555 from the PET wouldn't be that bad a deal, and I could obviously just put a little tiny perf board or something stuck around here and connect that to the motherboard and we'd be good to go. Now, as great as a 555 timer is, this is 20 of 24, and there's actually something that I can use that's a little bit easier to do, and it gives me some software control of things, and it's this, an Arduino Uno. I have a box full of these things. I haven't used these things in ages, and that's because, you know, they're a little outdated at this point. I think these have, been out for like 10 years now at least. But the great things about this is that they run on 5 volts. It's really easy to implement. I can do software control, so if I need to do additional stuff for debugging purposes, like say keep toggling the reset circuit continually, I can do that really easily with this. And if I get this system working and it comes time to making the reset circuit work properly, I can do one of two things. I can try to fix the power supply again, or I could just get like an AT Tiny, and I have a bunch of those. They're just a tiny single chip implementation of what you see here with only a few IO pins. And that's enough to basically hook up to this front switch right here to have the reset input and essentially control the whole reset circuit with a microcontroller, and it would work perfectly fine. So what I did is I whipped up a quick sketch for this thing. It's very simple. All it does is when this thing gets powered up, it waits 1 second and then it brings pin 2 out of reset, pulls it up to 5 volts. I'll just connect that back to the reset line like I was doing in part 3 through a resistor, mind you. I don't want to hook the 5 volts of this directly up to this circuit in case something goes wrong here. And I added an extra little feature that if I plug a jumper link like this between pin 3 and ground, what that will do is it will continually reset the system every, I think I had it set for 20 seconds. And obviously I can plug this into the computer to change that timeout if I need a different value. And the reason why I implemented this constant reset thing is if this thing runs its diagnostic and then it fails, I want it to just restart itself. And I want to keep doing that so that I can start probing around on the motherboard looking for faults, and the system will keep running the diagnostic. As it was before, it does the diagnostic once, halts, and then that's that. I would have to turn this computer off and on, or turn this to the reset position if I hook this signal back up to this Arduino, for instance. So why bother with that? Well, let's just do it in an automated fashion. There's the Arduino. I have it hooked up to 5 volts on the power supply connector, and then I have it hooked up to the reset input pin on the clock chip here, and that just feeds the entire reset circuit, and that's going through an 800 ohm resistor, which is what I was using last time. That seemed to work. As far as the state of the rest of this thing, I actually have all the various other components unplugged from the power supply, so only the motherboard is connected. The SCSI cable is connected here, but let's just get that off of here. We don't actually need that for this first test. I do also have this multi-bus expansion chassis connected, but that second power supply, I've actually never powered it up or tested it. It's not connected to this. So that resistor board is installed in here, but that doesn't do anything. That is actually just for the power rails to burn extra power if you're using that second power supply and you don't have any multi-bus cards installed. This machine supports up to 3 additional multi-bus cards, and I think cards that they intended you to use with this thing were additional serial ports up to 8, and then Ethernet board, and I think there was another communication processor type board. Anyhow, it's time to power this up. We know that when it goes into the failed state, the second LED here, which you can just see the back of, will flash. And let's turn this on, see if this comes out of reset. There we go, came right out of reset, just like that. I think this means I should get the serial cable plugged into it so we can at least see what's happening on the computer over there. So the serial cable is connected, and I'm not really getting anything on putty here. So what I need to do is put that jumper link on the Arduino between pin 3 and ground, which should restart the computer, and then we can hopefully see at least the Plexus banner. Okay. I put the jumper in place. As you can see, it is now running the self-test. Okay, same exact error we had before. So, oh, look at there, it's rebooting again. So that's great, that works. Alrighty, yes, I think the code has a 10-second delay. And yes, there it is right there, delay 10,000, so waits 10 seconds, which is actually a good amount of time. I could probably shorten that a little bit because this self-test seems to fail so quickly. And then, well, it helps me poke around a little bit more. Since the Arduino was a success, I decided to get rid of that, and I loaded that same code onto an AT Tiny 25 and I soldered it directly onto the board. Well, it's actually in a little socket. That means I can remove it if I need to change the code on it, like to add extra functionality or whatnot. But this little chip does the exact same thing the Arduino does, which basically fixes the reset circuit. All I need to do to complete this is wire up the output of this switch here that when you turn it to the reset position, it actually just grounds one of the signals here, which used to go to the power supply connector. And I'll just wire that directly to the ATtiny here. It has internal pull-up resistors for the inputs, which is enabled. So all I need to do is ground that pin, and then, well, we're off to the races. I can either have the code do the reboot cycle like we have now, or I can change it to just reset the machine until you put it back to the run position, which is the original configuration. So where are we right now? Well, let's be honest, that reset problem, that was low-hanging fruit and actually very easy to fix, which is a little bit of a hardware problem. The bigger problem is, how do we get this computer booting again? Let's think about an IBM PC BIOS. It has similar diagnostic codes that can fail when you first power on the machine. Because the BIOS is really well understood and all of those codes are documented, if you get a code when you first turn that machine on and it just halts, well, you could just look up what the code means, and if it tells you there's a problem with, say, the keyboard controller, well, you know where to focus your attention on the motherboard. Now, even if you didn't have schematics for the motherboard, typically the keyboard circuit is relatively easy to understand because, of course, the keyboard plugs into the back and you can just look at the traces and they'll go to one of the chips on the board and you can go backwards from there. But with this computer, we have a couple really big issues. The first is we have no idea what any of those diagnostic codes mean. The code we're getting is 4F02. What does that refer to? Who knows? But even if we did know, how do we know what part of the motherboard is the problem? Now, if it was something simple like a ROM checksum, okay, well, we know where the ROMs are and we can just, I don't know, try to swap those out or whatever. But if the code is pointing to some type of a logic fault on the motherboard, well, take a look at the board. There's a ton of logic on it, and lots of the logic has been condensed into PAL chips, programmable array logic. And there are, I think, 8 of those PAL chips on the board, and one PAL chip can take the place of a whole ton of TTL logic ICs. And that means those PALs sort of obfuscate a lot of the functionality that would otherwise be laid bare by TTL logic chips because you could just look up what they do. And that's all hidden away inside PAL chips. When this thing broke, I was honestly feeling a little despondent. Looking at this board, it's just a huge unknown mass of chips. There are 6 layers to the PCB. That means you cannot just look at traces running around the board because they often go to a via and then go to an inner layer and you don't really see where it goes. That means if you have a chip that you suspect is bad, like let's pick this one down here, to figure out where all of the pins go on this, you have to essentially clip onto one of the pins, say pin 2, and then touch every single pin on every single other chip on the board. Well, you could skip the VCC and ground pin, which are usually 2 obvious pins. And then you have to write down every single pin that has continuity to that chip. You write down the chip number, the pin number, and then you have to go through and reiterate that process through every other pin except for the ground and the VCC. What that's called when you have a pin on one chip that goes to a pin on a bunch of other chips, it's called a net. And when you're designing PCBs, you have these things called nets, which essentially have a name, and then it has a list of every chip and every pin that those signals go to, and you can imagine that there's actually traces running around the board everywhere that go to all these various components. It can also go to resistors and diodes and other types of passive components on the board as well, but really to start to reverse engineer the functionality of the board, you have to go through that entire process. It can be a little more difficult as well if you have a board that has actually suffered some damage, like battery leakage, because it can eat through traces and it can do that on inner layers as well that you might not realize. So when you're figuring out the nets of the chip here going to every other pin on the board, you might miss some stuff because that connection is already broken. Unless you have a board that is 100% operational and has no damage, you can't be 100% sure that you're not missing stuff. This board also has all sorts of bodge wires, which means you have to make sure you take those into account as well, because clearly some traces have probably been cut, definitely some pins have been lifted to install these bodge wires. So that right there is one of the first barriers to try to figure out how a board like this works. Now, when you do reverse engineering on a system like this, you have to do it methodically where you would say, start from the clock circuit. And there's a crystal oscillator up here and there's another one down there. So we have at least 2 clock circuits on here, and you start to trace that out. Typically those clock circuits will get divided down by some logic, and then those clock signals will make their way all over the board. You can then start from things like the CPUs, because we know what all of the pins on the CPU do, address bus, data bus, stuff like that. You can start figuring out those nets to unravel the mysteries of the board. There are other parts of the board that are obvious about what their function is. There's a connector right here that goes to the RAM board on the back, so we know there's data and address bus signals that go to that. We have some static RAM chips right here that probably provide some amount of memory that the computer or the processors can use during operation of the system. But there's also a bunch of static RAM over here, which is used for most likely a different type of function. This is much faster static RAM than the stuff that's over here. So this stuff is probably used for a memory mapper function, which has to do with protected memory and virtual memory that needs to be implemented to properly implement a Unix system. There are also these 74-154 chips right here. There's 3 of these, and these are almost always used for select logic on various motherboards. So you can start to tone out the nets that are connected to that to try to figure out what peripherals and whatnot are selected by these chips. Probably things like the serial ports over here and the RAM and ROMs and stuff like that. So familiarity with the way these types of systems are typically designed helps a little bit in just trying to figure out the fundamental blocks and areas of this system. But when you look at this area right here, it's just a whole ton of TTL logic. And you know, some of this is going to be built for implementing the SCSI, some of it's going to be select logic for, say, the serial ports, but a whole lot of this stuff around here is probably used for the memory mapper function, which is that virtual memory thing I talked about that uses this SRAM. And it's not really easy to tell with this system where those chunks of the board are. Like the mapper stuff might be all located right here around the SRAM, but it might not be. It might be over here too and over here, and you know, it's really hard to say. Now, the reason why I'm talking about all this is because, as I mentioned, this is only half of the problem. Understanding how the board works and the nets and the schematics or the lack thereof, that is solvable by a whole ton of work. The other half of the problem is understanding the diagnostic routine that's running and to see what is it doing when it fails. That would give us the clue of where on the board we could focus attention to try to get this thing working. Now for me, hardware, like doing the reverse analysis of the motherboard, is time consuming, but it's totally something I can do. But understanding how 68,000 code works or 6810 code works in these ROMs to unravel the mysteries of that diagnostic error code, that is way above my head. I was just feeling pretty despondent because, well, initially when that happened, I just thought, how am I ever going to figure out what these error codes are? I'm never going to be able to do that, at least on my own. So I was talking on the phone to David over at Usagi Electric and mentioned that this machine had this problem now and that I really was stuck because I have no idea how to reverse engineer 68,000 ROMs. And he suggested reaching out to people on his Discord server. What we decided on doing is creating a Discord channel on his server, because I don't have a Discord server, and asking people there if they could help with some of the analysis of the ROM code on this thing to give me the clues that I needed to figure out the hardware fault. So that's exactly what we did. We created a new channel. I put a note on my Patreon to have anyone come over from there who was good at this kind of stuff. And then he's already got a ton of people on his Discord server that are good at this sort of thing. And I went in there and I asked the question, hey, we have a machine here that is failing its diagnostics, and I really could use some help to figure out what it's doing when it fails. So I uploaded the ROM code that I had dumped from part 1, and people got to work in Ghidra and started analyzing the ROMs. Now, parallel to that, I have the hard drive image that I took from this machine, and I've had a few people ask why I haven't posted the image online yet. I posted the ROM code and anything else that I found about this machine online, but not the hard drive image. Well, the reason why is I asked a few people to start looking at the hard drive image that I took with the emulator. I wanted them to start looking for anything that looked like PII or personally identifiable information on there. I don't want to have people's names and addresses, especially if this was a business computer used in operation of a business. It could have people's social security numbers, it could have addresses, names, all sorts of things. And I don't want to just go and upload that to the internet. That is completely irresponsible of me. And because the computer had failed, I could no longer look around the hard drive myself to try to see if the information was there. I didn't get a chance before this thing broke. So in parallel to everyone on Discord starting to reverse engineer the ROMs, I had trusted friends starting to look at the hard drive. And boy, did we find some interesting stuff on the hard drive. So I've printed out some stuff here, just some notes for myself, so I can try to keep all of this straight, because a lot of this was all happening in parallel on Discord and offline with the hard drive analysis. So for the hard drive, it did appear that it looked like there were a few different user accounts on this machine. And what I didn't really get to, it looked like there was some kind of an office suite on here, like a word processor type thing installed. And almost certainly this was just used for that type of activity. But what's really interesting is that the folks who were doing this analysis actually came to the discovery that there seemed to have been some other stuff on this machine that actually pertained to technical documentation for the computer itself. But the strange thing is it wasn't on any of the partitions. There was the root partition and there was a /user partition. It appears there's also a third partition on the hard drive that is almost like a system restore. It's like a virgin copy of the operating system that was called, I think, stock U. That did not get mounted when I booted the system up, but it was there on at the end of the hard drive. When the folks analyzing the hard drive started to use forensic type tools on it to look in what was ostensibly the free space on there, we started to actually find other documents. To make a long story short about accessing this data, and don't worry, I'll post a longer, more in-depth analysis of how it worked once we're able to clean up the data on the hard drive, sanitize it, get rid of the PII, stuff like that. What happened was, it seemed at some point this computer was being used by someone who actually worked at Plexus. And the funny thing is, it seems the computer was repurposed for, civilian use, let's just call it. I mean, it's not military, but, not company use. It was going to be used by someone outside of the company. I think the machine was end of life at that point, and they just wanted to reuse it. So what happened is that person went to repartition the hard drive to erase that /user partition that had all the documents and stuff from its original use and created a new one for its new life and its new purpose. Now here's where things get wild, and this is honestly a stroke of luck you would not believe. The user partition on this drive started, I think, at block 60,000. That was the original location of the original user partition on this machine. Well, the new partition that was created for this computer's new life in office work was actually created most likely by a typo at 66,000. I might be leaving off a trailing zero there, but either way, there was a typo. Instead of 1 6 and a bunch of zeros, there was 2 6s and a bunch of zeros. So the new user partition was created and formatted it and set up for its new life, and that's where people put their office files or whatever. That original partition, though, was still there. It was never erased, it was just repartitioned, and instead of erasing the original partition and formatting it, it was created at an offset. Now, when this system booted up in part 3, it was mounting the new user partition, the one at the 66000, a bunch of zeros, and not the original one without the 2 6s. So with some forensic tools and then some other fanciness with old source code from System 5 and stuff like that, the people working on the drive recovery were able to access the files that were contained in that original partition. And it seems about 80 to 90% of them were not overwritten. I guess it wasn't that a ton of data was ever stored on this, so when the new partition was created with that offset, it actually didn't affect most of the files in that original partition. And because the original partition still had a super block and all the parts that make up a Unix file system, it meant even the directory structure was intact. So we didn't just have file names, we had an actual directory structure. Now, I'm not ready to release all the files that were in that hidden partition because just like in that later user partition for this computer's new life, there was also PII in that first partition. But what we could ascertain is that this computer was actually owned or used by someone at Plexus involved in the design of this computer. It's completely mind-blowing. Honestly, when we started looking at this data, we could not believe what we were seeing. And the reason why I say that is because in this directory were technical documentations about this computer. There were the equations for the PAL chips. There were the net lists, that is that list of all the connections between every chip. There were parts lists. There were technical documents outlining the memory map, the register map, the functionality, like the basic functionality of this, all the pinouts of all the ports, including this one here from multibus, and there's a diagnostic port down here, and the SCSI, and everything. It was all in there. There was even documents in there talking about the modifications required for the prototype machines to make them work. And all these baud wires that are on here were described in technical documents because the person, I think, who was using this machine actually worked on troubleshooting the prototypes. And while I don't think this is a prototype because the serial number on the motherboard here is like 100 and something, it's almost certainly one of the early run boards, which is why it has all these baud wires that were done after work by this person who worked on the design and did the troubleshooting for it. So we had just struck a literal pot of gold when it comes to this machine. Now, if we could figure out what the ROMs were saying when it came to that error code, that could actually give me a clue as to where it is. And now that I understand, because we have these files, they're just text files, mind you. We don't have like a PCB schematic in a graphical format. You have to remember this was in 1984, I think, when this was designed. But we now have all the information needed to go from one chip to every other chip on the board because it's all contained in these files. I cannot express enough how much of a lucky break this was. This was unfreaking believable that we went from a computer that essentially had no technical documentation of any kind, just like a couple page pamphlet just outlining at a very high level what it was, to now having pretty much everything that's necessary to recreate schematics for this thing with enough work, and even go as far as create an emulator for this. Since I have the equations for the PAL chips now, that deobfuscates all the logic that's contained within them, and we have all the memory maps and all the other stuff, and we obviously have the ROM code, and we have a working hard drive image that can boot the system. Emulation is actually possible. So back on the Discord channel, I shared some of the information that we found from the recovery of the hard drive, including the memory map and a lot of the registers. And registers, if you're not familiar, they're essentially, think of them as a bunch of switch settings, but they're, instead of being physical dip switches, they're inside a latch chip. And what that latch does is when you set it, those values that are set, those bits on or off, stay there. And later, what the system can do is you can query the switch settings, so you can go and read what's in that chip, but also those chips can take action on various components on the motherboard. So for instance, you could imagine there could be a soft switch. We'll call it a soft switch for, say, diagnostic mode. When you set that in the register, then that can affect a bunch of logic that could change the functionality of the board. Well, most computers, including this one, have a bunch of these registers, and they do all sorts of different things. And understanding what those do is extremely helpful when you're trying to look at the software. The ROM is going to boot up and it's going to change modes of operation of the motherboard and whatnot, and that's all going to happen within these registers. And in that technical documentation was exactly that. A list of the registers, the memory maps, all that stuff. It was an unbelievable stroke of good luck that really is just almost impossible to comprehend. How lucky we were was unfreaking believable. So, armed with the knowledge of what the registers did and what the memory map of this entire processor address space is, remember these processors can address 16 megabytes of memory. With that knowledge, over on Discord, the team using Ghidra to reverse engineer the ROMs were able to ascertain that that error code that I was getting when I boot this thing up, or I am still getting when I boot this up, is the fact that it is unable to see any RAM. Yes, it cannot talk to the RAM at all. It does some routine that tries to scan for the RAM and then test it. And when it scans for RAM, it finds nothing. It finds 0 RAM. To help validate that hypothesis of what's wrong, I took this machine apart. I didn't record this or anything, but I removed the RAM card from the system. And sure enough, that error code did not change at all. It was identical error code, and it happens in exactly the same amount of time. So I had a lead as to what's going on now. Now here's where things get a little bit more complicated. On home computers using the 68000, imagine like a Macintosh or an Amiga, there's no protected memory. That means that any process running on your processor can access any part of memory. It can erase RAM, it can do whatever it needs to. There's no protection where, say, the system OS can say, hey, this RAM is protected, don't write to this. Because if you do, you're gonna crash the computer. But obviously, when you're using a multi-user computer like this, that has multiple people logged in, you need a way to have private memory for each of the users so that you don't overwrite each other's RAM and you don't crash the system for everyone. Well, what happened on these early multi-user Unix systems that used processors like the 68000 or the 6810 that didn't have that memory mapping protection stuff built in is you had to implement your own memory mapper on the board itself in hardware. Now, later versions of the Motorola 68000, I think the 68020 or maybe the 68030, it had that built in. That capability was all built into the chip, and that's why you started getting virtual memory and things like that later. Intel processors are exactly the same, 8086 and the 286. I think the 286 had protected memory, but it wasn't until the 386 that you really got full virtual protected memory where the OS could configure the memory management unit to give you more memory than you actually had that was virtual memory, and also protect memory to have protected operating systems, things like that. And that's why Linux and Windows NT require a 386 minimum, because those need those memory management units that are built in the 386 and up to do all that protected memory stuff. And that's the same on 68000 chips. A lot of the actual Unixes that run on these types of Motorola processors, like the ones on the Macintosh, require machines that have a memory management unit, either a separate chip or built in the processor. Well, 68000 and 6810, it doesn't have that. So this computer has to implement a mapper in a bunch of logic on the motherboard, and that's exactly what all this SRAM is. When I was talking earlier about the constituent parts of the motherboard, that hypothesis was confirmed that this was for the mapper based on information that we saw within the technical documentation that was recovered from this hard drive. Now, for troubleshooting at a hardware level, what would be really essential is having schematics, because that is a visual representation of every connection, every net on the board that allows you to easily follow from one chip to another and make your way through the system to try to figure out where your hardware fault is, because clearly that's what we're dealing with right now. The RAM card's installed in the system, but the CPU cannot see it. Now, with more modern versions of PCB design programs, they can create these net lists, text files that list out all these connections between all the chips and stuff like that. And you can take those files and re-import them and turn it back into a visual schematic, you know, with a bunch of work laying out the board and stuff like that. The problem is, this board was designed in around 1984, where we didn't have tools that we do these days. And it seems that the tool that was used to lay this out was called Kale. I might be mispronouncing that. I think it was a German PCB design piece of software that ran on the PDP-11, the DEC PDP-11. So those were the files that were left behind. And unfortunately, it seems like, at least initially, no one has been able to take those files and load them into, say, KiCad to turn this thing back into a schematic. One of the users on Discord was manually taking these net lists and looks like recreating the ICs in KiCad, but it was an entire manual process. Looking at the files, these text files, you got to cross-reference the parts list file versus the nets file, and then rebuilding the chips one by one. And obviously, once you've rebuilt everything, if you have all those nets labeled properly, all the chips can be reconnected pretty easily. This machine appears to have over 1,000 nets. And remember, the net is where one pin connects to several other chips. That is a net. You could just imagine it like a little net across the board. There are over 1,000 of those on this board. And all of that has to be recreated by hand, because it doesn't seem like there's at least a way right now to import those tools. So what I had to do to start reverse engineering how this was working is trying to think about some of the reasons why the main memory wasn't accessible by the CPUs. Now, my first thought was that the memory mapper, the MMU that's designing hardware on this, had a failure of it of some kind. And without that, the system wasn't going to operate. That the CPU needed to talk through the memory mapper in order for the RAM to be even reachable. The technical docs were not clear on exactly whether that was the case or not. It did say in there that you had to have the memory mapper enabled for the operating system to work, for normal operation of the system. But what wasn't clear is if the ROM diagnostic routine also relied on the mapper or not. So I went off the assumption that the mapper was going to be necessary, so I started looking into the logic of the mapper. Now, when we look at the technical docs for the system, there are signals in there like disable mapper in a register that lets you turn on and off the mapper. And I needed to go from the register and then start going backwards and figuring out what that does exactly. What physical effect does that have in the logic on here when you disable the mapper? Because we don't have finished schematics for the system, all we have is these text files. To do this reverse analysis, I basically had to do it on paper. Now, I did it in Notepad, or Google Docs actually. And what I would do is I would go to the first chip that was the register for that disable map signal, and I would have to lay out every pin on that chip, and I think it was a 373 latch somewhere around here on the motherboard. And I'd have to go in the net list and find every other chip that the disable map signal goes to. And once I found each of those chips, I had to go and identify off the parts list what kind of a chip it was. And then I needed to figure out if the signals on that net were going into those chips or coming out of those chips. Because remember, every chip has an input and an output pin, and some of them have both. If it's a transceiver chip, it can actually change direction. So first, identifying every chip what they are, going and looking up the pinout or the data sheet for those chips, figuring out if that pin that's identified on the net list is an input or output, so marking that. And that allows me to kind of figure out the flow. A lot of times a signal will come out of one chip on a net and it will go into a whole bunch of other chips. And then from there, you have to look at all those other chips and see where they go and what they do and follow that path all the way through to the logical conclusion. I could see that the disable map signal in the register ends up in one of the PAL chips as an enable map signal, which has to do with turning on the entire mapper circuitry or turning it off. And I needed to make sure that when that register was being set high or low, that the signal making its way all the way to the PAL circuitry that turns on or off the mapper was working correctly. You can imagine that the ROM code might be telling that register, hey, disable the map and then turn it back on. And I could go to that PAL chip now having analyzed the entire flow of the signal through all the chips. And I could say, oh, I know now that when that disable signal on the latch is high and these other situations are met, the signal on the PAL chip should be low. And if it's not, like it's high all the time, even though the signal over on the latch is changing, then I know there's a fault in there. And using the information that I reverse engineered, I could then go try to figure out where exactly that fault is. Now, having worked through the entire map logic all the way through to the end where the PAL chip actually turns it on or off, I was able to conclude that that whole circuit was working perfectly. As designed, when the system starts up, the disable map signal is low, meaning it's enabled, actually. And what the ROMs do during the diagnostic process, they seem to activate that disable map signal in the register, which then actually does turn off the memory mapper. And I guess that's just done so the processor maybe can talk directly to the DRAM without the mapper circuitry being in the middle. And when you look at the diagnostic test that can run on this system, there is a test that runs later that's called mapper. And there must be some test routines that then exercise the mapper to make sure that it's functioning properly. And this is all before the system can boot to OS. So it seemed that the memory mapper circuitry on this was working properly, and then that was not the problem. That had nothing to do with why the CPU couldn't talk to the memory. So where to look next? Well, I wanted to start looking at the memory card itself. Now, it's difficult to troubleshoot because the board needs to be installed in here because the power supply cable is short and the RAM card is on the back. So I can't easily poke around on the RAM chips. That's where the Discord user Super SVGA came in clutch. I don't use that word very often because I'm, not hip with the young people. Basically, that user took all the information in the net list and recreated this 96-pin connector here in, well, a visual diagram that listed every single net for every single pin on here. I could probe around here with my oscilloscope, but not knowing what each pin did, I didn't really know what I was looking at. Well, with this map right here that Super SVGA created, I was able just to methodically go through all 96 pins and I wrote down exactly what I saw. And that would allow me to later go back and do analysis on, well, what these signals were to then figure out what seemed wrong. The gist of what I found on this connector is it has two data buses. One 16-bit data bus goes to this processor, which is the DMA processor. Now, DMA normally stands for direct memory access. I don't know what it stands for in this case. Maybe that's what it stands for as well. But nonetheless, this processor is the one that runs the diagnostic code, has access to all the I/O. It's what's active when you first turn this computer on. This other processor is called the job processor. And at this stage in the diagnostics, the people who reverse engineer the ROMs could see this processor is not doing anything at all. It's completely inactive at this point. So looking at the two data buses that were on here, I could see that the data bus that goes to this chip was busy. It had lots of normal activity on it, all 16 lines, but the job processor data bus, there was nothing happening whatsoever. And that was completely expected and is exactly what I thought I would see. Now, the other types of signals that you see going to the RAM card are address lines. Now, there are not two sets of address lines, only one set of address lines that goes to the RAM card. So obviously, because both processors can obviously talk to the RAM, there's logic on here to switch between the two processors. And when I went through all the address lines on here, there was no activity at all, none. So of course, with no activity on the address lines, A, you're not going to have any DRAM refresh, so the RAM can't even work. But then worse than that, clearly without address line activity, the processor is not going to be able to read or write from the RAM at all. Nothing is going to work. And most of the RAM signals were either low all the time, or some of them were just high all the time. And occasionally some of them were pulsing, I think with the reset signal. And I was using the Arduino to reset this thing. So that is a huge smoking gun for a problem. There's no way a system can work with no address line activity at the DRAM. And that's obviously why the RAM test was failing. Hey, I can't find RAM. Well, yeah, because there's no address line activity going to the RAM. And that brought me to the next phase of the diagnostic process. And it was exactly the same as I described with the map, going backwards through the signals. I picked some random nets on the RAM card connector here, various address lines, and I started going backwards to see how they work exactly. And I noticed a few things. The lower address lines, 0 through 11, they're only connected to a multiplexer, and the multiplexer seems to select between either of the two processors. The higher address lines, on the other hand, go through the memory mapper circuitry here, and the memory mapper circuitry is allowing, I think, 4 kilobyte pages of memory. So the minimum page size is 4K. And that means that the SRAM down here contains a map of all the memory that the processors can use to move memory around and create virtual memory and stuff like that. And yeah, 4K is the minimum size. So I decided to ignore the mapper circuitry and just focus on those lower address lines that go to the multiplexers, because even those lines, according to the oscilloscope that I hooked up to the pins here, those lines were just always low all the time. So clearly something was wrong. So I started reversing all those signals and just going backwards through everything. And I found the multiplexer goes through several different ICs along the way, and it goes through a PAL chip even that has to do with enable DMA, an enable DMA signal. And remember, DMA is this processor here. This signal obviously is used to allow this processor to communicate to the RAM. And I guess what happens is it gets turned off and on as the RAM access happens, where it allows the job processor, when it's running, to also talk to the RAM, you know, odd cycles or whatever. It switches back and forth, I guess. So when I took a look at the enable DMA signal on that multiplexer, this is the one that selects between the two processors, I could see that that signal was not changing. And that would mean in the idle state that that chip was in, when the machine was on, is that the RAM would always be connected to the job processor. It would never be connected to this one. Well, that's clearly not right. I don't know how that should look while the system is operating, but I know enough to know that when you look at the logic and the truth tables for the multiplexer, in the way it was here, it was never going to be able to talk to this because the enable DMA signal was never being set. So it was just a matter of going backwards through all the nets and all the chips that generate that signal. The enable DMA signal came from a PAL chip. I think it was this one right here. Has a bodge wire on it, but all the connections to that chip look good. And looking around at that chip with the oscilloscope and mapping it all out on the list here, everything else that was going on that PAL looked correct, but it looked like some of the signals that go into the PAL that have to do with selecting or deselecting the DMA functionality of the RAM, those weren't changing either. So the problem was upstream from this PAL. If the PAL were bad, and keep in mind, I didn't know at the time that we had the equations for this PAL, so I thought, uh-oh, if this chip is bad, we're completely screwed. But the reality is I could recreate this now because I think we have the equations for it. By the time I didn't know. So anyways, it looked like the PAL was still working, and it was the input signals into the PAL that were actually bad. So I just kept going backwards. And after going through some more chips, what that led me to was a flip-flop. And the flip-flop, which incidentally is right here, under where the battery is. That flip-flop is supposed to be generating a signal that tells the PAL chip to enable the DMA, and it looks like that signal wasn't working correctly. In fact, on the oscilloscope, I could see that there was a little bit of it trying to go down to ground, but it was just stuck around 5 volts. It was like going down a little bit, but not working. Now, one of the things about flip-flops is that there are 2 flip-flop units in one chip. So there's 2 separate sets of functionality happening. The other half of that chip working perfectly. You could see everything going swimmingly and working well. But the other thing about the flip-flops in here is there are 2 outputs, and one's an inverted output from the other. Well, one of the outputs goes to the PAL, and the other one goes to some other stuff on the board. And the one that was inverted and going to other stuff on the board, it was working. I could see it, you know, pulsing and looking normal. And it sort of was going in these bursts, which I guess are the enabled DMA signal. But the one going to the PAL chip, and it only went to the PAL chip, it was not working. It was just only slightly going down. It looked, well, it looked suspect. In absence of knowing the critical function of the flip-flop going down to 0 volts to enable the DMA processor and stuff, I don't know if I would have thought that that was a bad signal. It looked slightly suspect, but not really, because TTL can be kind of noisy at the top and the bottom. That's normal. That doesn't break operation of a system. And as I said, the inverted output of this flip-flop going to other things was working. That meant that the inputs that are going to the flip-flop are fine. Those whatever signals that go into it are actually good, because those 2 outputs of the flip-flop, they're just inverted of each other, but they need to always mirror each other. There's no way that they would ever be different than each other other than one being the opposite signal. So with that flip-flop looking like it was the smoking gun, the thing I could do to try to validate that the flip-flop is the bad part and not the PAL chip is actually take the PAL chip out of the socket, because it's in a socket, and lift the pin on the PAL that is going to the flip-flop. And according to the net diagram in the documentation we uncovered, there are only 2 things connected to that output of the flip-flop. Well, one thing really. It's the flip-flop itself and the PAL. That's it. It doesn't go anywhere else on the board. So when I lifted pin 3 on the PAL, and then I probed the flip-flop for that output, it still was screwed up in exactly the same way. No difference. So it was not the PAL chip that's forcing that output to be held at 5 volts. It was without a doubt the flip-flop. And to recap, the flip-flop generates a signal based on some other signals that tells the PAL chip that the DMA circuitry should be enabled for the RAM access from the DMA CPU. And because that signal was never going down to ground, the PAL never thought to turn on the access from the DMA processor to the RAM, which means that the processor had no way to ever talk to the RAM, and none of the address lines here would ever do anything because the job processor is not running at this phase of the diagnostic. Thanks to everyone on Discord, we know that. And that's why I saw no access here, and that's why the processor had no ability to talk to the RAM. So that catches us up to where we are now. I didn't record any of this troubleshooting process, unfortunately, because I don't know, I just didn't know where I was going with this, and I didn't know if this was going to be, 5 hours of work or 500 hours of work, and it's very difficult to take 500 hours of footage and turn it into something. So that's why I'm giving a little bit of a recap now with the story of how I got to this point. The flip-flop is still installed in the board. I haven't done any further repairs at this point, but what we're left with now is actually time to take the flip-flop out of the board. I have another one. I found another one. It's a 74S112. I also found some LS parts, but the S parts are faster. I found one of my spare parts. We need to stick it in there and see if this fixes the problem. So let's go back to real-time troubleshooting. I'll get the motherboard out of here and we'll get this chip out of here and we'll see what happens. All right, the motherboard is on the bench, and since it was over in that computer, you may notice I actually added one extra bodge wire right here, and that is the reset signal that comes from the switch. The switch grounds the reset line that used to go to pin 2 on the power supply connector, but I cut a trace right there. I drew an arrow so I could tell where that was. I cut a trace right there, and then I connected the bodge wire over here to the AT Tiny so that the reset switch is connected to that, which means I can either engage the continual reboot mode, or if I change the code, it will just reset the computer. And if I put it back to run, it'll just continue to work. What we're here to work on though is the flip-flop, which is this one right here underneath the battery damage area. Now I alluded to the fact that I wasn't surprised once I figured out that this was the chip responsible for generating that signal, and it has gone faulty. Because originally the battery corrosion, you can see a little bit left on that connector right there. It had dripped down onto this chip, and a couple of the pins over here on the right top side were crusty. Anytime there are crusties around one chip, be very suspicious that that could be faulty. And I probably could have saved myself a little bit of effort if I went to this chip and I went to every pin on the oscilloscope and just looked at it. There was another one over here. I think this chip also is a bit crusty. This Motorola part here, it's a little bit of leftover hot glue there. So checking everything on here might be a good idea as well. There's still a little bit of crustiness around here from that battery leakage. It didn't seem so bad, but obviously it did cause some damage because, well, this chip failed. Of course, we don't know for sure if this is the only fault on this board right now, but it stands to reason that it is the one, because it's definitely a signal that's related to what's wrong with this board, and it's not working. And I went into my parts bin and I found these replacement chips right here. The top one being an exact drop-in, an SN74S112N, and these two are also the flip-flops, but they are the LS parts. So of course I'll start with this one here. I do know that these two work, these lower two, but this one's untested. Looks like it's never been in a computer though, or at least it's just been in a socket. So hopefully it's a good part. So this board has obviously a very thick flood fill for both ground and 5 volts all over the PCB. It's one of the ways this thing can run so fast is because it has all that grounding in there. That means that desoldering stuff is going to be extra difficult, so I'm going to use hot air to heat up the board while I use the desoldering iron at the same time, and that's going to help get everything out of here. All right, the socket is installed. Let's make sure we don't have any shorts. All right, those two are shorted. Not sure if that's on purpose or not. I'll have to go compare to the nets. The traces are very close to the pins, so you do have to be pretty careful with these vias that are here. Okay, I think everything is okay except for those 2 pins. Let's flip it over. All right, from the top side, it is these 2 pins that are shorted. Going to my notes, here's the flip-flop, and yep, 14 and 15 are both hooked up to PU7. It's a pull-up resistor, I guess. or a pull down resistor or something like that. So just double checking that that's those 2 pins, and that looks good. This is the chip that I removed from the board. You can see a little evidence of the crusties that were right there. And it looks like it's crusty on the other side as well, at least on the underside. You can kind of see it's a bit crusty there. So we'll just straighten the legs on the new part that's going in. In goes the new chip into the socket. Compared to the old part, looks similar, although 323B on the old one and 332B on the new one, plus a yellow dot. And now it is time to reinstall this large motherboard into the computer, and let's see if it works. And this is the putty terminal I was using before. Now I found with this particular computer, if I let it go to sleep and then I wake it up again, sometimes it doesn't work, even though we're on COM2 here, so a physical COM port. So I'm just gonna restart putty, because I would like to make sure that as soon as this starts to boot, we see exactly what's happening. All right, I have the camera positioned so you can see the LEDs. We can see if it goes into the failure mode. Here we go. Came out of reset, that's a good thing. Oh, we got Plexus on there. Here we go, everyone. It's about to fail if it's gonna fail. And the original test took way longer. Oh, this is good. This is freaking good. Here's the bad chip right here. Yeah, this would have failed by now. It would have had the error 4F02. I have like nightmares of that error code. I think this thing is gonna work again. Now, hard drive's not connected, SCSI's not connected, the power's unplugged from everything. So if this thing gets to the actual, oh no, oh no. This might not be a problem. Let me grab the keyboard here. I know if I hit the exclamation point, yes, you can exit out of this. This is stuff that the people on the Discord server figured out. So we're actually at like the boot prompt. Okay, well, it's trying to access the SCSI device and that's not there. So even though we had a clock failed and multi-bus failure, I think those are not critical errors. At least they're not critical like the RAM error was, because when I push exclamation point to exit out of the boot sequence there, what would happen is it would just immediately fail again because the system needs main memory for this thing to operate. And I don't think multi-bus and the clock working are that big a deal. And we have seen those errors before and they're sort of transient. Let me try to see if the reset works, the extra wire that I ran to the AT Tiny. So turn it to reset. Yes, it works. It went to reset. Turn it out to reset. There it goes. That's cool. That actually works. Yeah, the code that's currently on the AT Tiny is actually just normal code, meaning when you turn that to reset, it just resets the computer and it will fall out of reset as soon as you take the switch away from the reset position. So cool. We've replaced the whole power supply flaky reset circuit. Oh, config invalid. Yeah, I can exit out of this. The config invalid means that the clock chip itself is corrupted. There's no battery in here, so maybe that's that particular error that's just getting. I don't know. Okay, you know what? Let's plug the hard drive back into this thing and let's see if we can even boot this thing up. All right, I've reconnected the SCSI drive, the interposer, the tape drive, and the floppy drive. Let's turn this thing back on. And yeah, we're getting those errors again. All right, self-test failed. I hit exclamation point to bypass. And that is it. It's booting. Yep, hard drive LED is blinking. So we are back in business, everyone. We are back in freaking business, I hope. Let's just see if this thing actually works though. Maybe those other 2 errors are actually so serious. Hey, I just realized, well, it is booting. It does say 2 megs of RAM. So before, when we weren't getting any error messages, it did actually show us how much RAM we had. It had some other information that did print, but now it doesn't print and I have to break out of the self-test with the exclamation point command. Is it frozen right now? Unfortunately, it looks like it is, everyone. Oh no. Yeah, we are stuck now. I'm pretty sure it booted more quickly than this. It got from the memory area here into the OS. It was like mounting the drives and stuff like that. And now it's just sitting here and doing absolutely nothing. Kind of has me wondering if the Unix operating system is trying to talk to, say, the clock, and I'm assuming it means the clock chip, and it's not able to, and that's why it's hanging here. As far as the multi-bus failure, well, I couldn't even explain why that is. I'm going to give a push to some of the socketed chips on the motherboard, like the PAL chips, because a few of them I've sort of jostled since I've been working on this thing, and give this thing a few reboots and see if I can get this thing booted. Well, unfortunately, I did a whole bunch of poking around, sort of fiddling with the board a little bit. Even put the multi-bus card cage thing back in there. Didn't make a difference. This thing is still unhappy. We're much further along than we were. We're getting working memory. It's actually trying to boot the OS, but it's hanging up. And my guess is it's hanging up on the clock. That error about the clock is probably the clock chip. And since that's up in the battery damage area, I'm gonna have to do some investigation.
It's time to sleep on this issue and see what I can figure out in the morning.
All right, so I want to address a couple things. A few people pointed out that I probably needed to have the multi-bus expansion installed on the front in order for the system to boot without an error, and that this board needed to be installed. This board's only required if you're using a second power supply. There's a connector right here that can go to the power supply, and that feeds the pins that go to the back plane that supply power to the other cards. So you can either connect the power supply here, or you can connect the power supply directly to the back plane, because it also has a power supply connector. Now, when you look at the backplane, because you can see the traces clear as day, the power supply connector on the backplane also just goes to these same pins right here. They don't feed the motherboard. The motherboard has no idea that power supply is there or not there. It just feeds this card. Or obviously, if you have any other multi-bus cards installed, it will feed those with the requisite power. I'm assuming normally you would plug the power supply into this if you're using this board, just because you're not going to put any stress on the traces that are on that multi-plane backplane. The power that goes into this connector will just be turned into heat through all these resistors. But obviously, if you're not going to use multi-bus, you don't even need this, and you just unplug the power supply, which is what I've done, and that simplifies that whole process. I had this thing booted up into Unix without this card installed. This thing was never in the machine, and it was definitely running Unix without any kind of issue, and then we had the failure of the chip on the board. My assumption is that this system came in two configurations. One didn't have any of this multi-bus stuff. This was missing, and so was that second power supply. So the motherboard obviously has to work properly without these installed because, well, that is the P15 configuration. This is the P20, which means it came with this, and that extra power supply. And if you're going to run everything together, then you just need to make sure the resistor board is in there so the power supply doesn't have any regulation issues with this all installed. Now back to the issues that this thing is having. We have those two errors. I think the first thing I need to do right now is power this thing back up, and let's make sure that it still has that same failure. All right, I have the key replacement, the screwdriver. It's like I stole the car here or something. Let's turn the computer on. All right. Is it coming out of reset? Yes, it is. There it is. So all the usual noises are happening. Self-test revision 3.3. I'm assuming this thing will fail in exactly the same way. Now back in part 3, when we had the problem where it couldn't talk to the RAM, this self-test would fail very quickly, and it would fail with that 4F02, that was unable to talk to the RAM. But now there it is, takes longer because I think these tests run sequentially, and it gets to the multi-bus and it says it has a failure, and then it gets to the clock and then it says a failure. I think it's running a couple more tests there. And yeah, it told us the config value or config info is invalid. What that's talking about is just like on a PC, when you fire it up, when there's no battery, you'll get like a CMOS checksum failure. You go into the CMOS, you configure it, save it, then everything is good. It's telling us that the config info is invalid. Well, of course it's invalid because the clock chip has no battery on it. And those Motorola MC1468818, that's the chip that's in there, when they're uninitialized because there's no battery on there, when you power them up, they just have a bunch of random garbage in there, and it needs to be configured by the OS or the ROM or whatever. And then with a battery, obviously that gets saved. Or usually with those chips, they stay running while the computer is powered up. So as long as you don't turn it off, you're actually going to have a valid configuration. It's just once you shut it off, it will lose those settings. Anyhow, I have validated the system is broken in exactly the same way it was, which is good. I don't like things when they spontaneously fix themselves. And this actually brings me to the next awesome thing that the folks on Discord figured out about this system. They have been consistently working on reverse engineering the ROM, and they have figured out that there are a bunch of commands that you can do to do things while you're in this ROM, even in the halted state that we're in right now. So let me demonstrate some of the stuff that they have figured out. One of the things that were figured out is that if you hit Shift and 1, which is the exclamation point, what that does is it exits out of the halt state. And you can see we're at the Plexus primary boot or version 1.2 prompt. Now, if I hit enter, it should load the Unix kernel and start booting the OS. And yes, that's exactly what it's doing. It should print how much RAM it has available and then load the system. And right here is where things go wrong. And I have a feeling it's probably trying to talk to the clock right now, which I don't think is working because it says clock failed. And that's probably why the system is hanging up right now. So I'm going to use the old screwdriver here, and let's reboot the computer by switching it into reset. So there we go, and out of reset. Okay, that's going to boot back up. That's my AT Tiny in there that's allowing that to happen. Now, here's another cool thing that they figured out. I have this terminal profile for PuTTY here configured to send Control H when you hit the backspace key. And that was because when it was booted into Unix in part 3, that's what I found it needed for me to have the proper backspace. But if you change it to this Control H or decibel 127, and I press the delete key, it drops us into a menu called DMA. Now, DMA, as I mentioned in part 4, the last part, that is the name of the processor that's running the diagnostics right now, the other one being job. And it seems that there are a whole bunch of commands in here that you can do additional diagnostics, which we don't fully understand yet. I did a bunch of button mashing in here. I was playing around with this earlier, and I found if you hit the T key, it runs all the tests, but it's gonna do it in a way that is going to be verbose. So it's actually going to give us info about what's running, as opposed to when you first power on the machine, it just says nothing until you get an actual error. So you can see it tested the ROMs, the static RAM, the SIOs. It tested the RAM, which was failing before, right? That was what we were stuck on in part 3. It's now testing the job processor, the map, the mapper, the SCSI. Here's testing the multibus. Let's see what happens. Multibus passed, but now it's testing the clock calendar. And yeah, check it out, config checksum error 85. So that's the error of the config checksum. I guess that's, I don't know, whatever, a specific error code. And then we get that final warning. But all of the tests pass except the clock calendar. So strangely, the multi-bus test passed. But let's talk about what we're seeing here with this clock output. So on this system, it appears that the clock chip is assigned to D0 and then 0000. That's where the clock chip resides in memory. The 68000 is a memory mapped IO system. It doesn't have separate IO address space like Intel systems. So every type of peripheral on this system has to be mapped into the main memory space. And it's a 16 megabyte memory space. So you have to carve out little chunks for the various systems, SCSI and the clock and whatever, all the different stuff. Well, this is where the clock chip is. And the DMA processor is obviously trying to read from the clock chip, which is incidentally only an 8-bit chip. And that's why it's skipping every other address here, because of course this is a 16-bit processor. Well, it's a 32-bit processor really, but it's reading everything in 16-bit chunks. But since it's an only 8-bit chip, it's only gonna happen on every other memory location. So it was trying to read out all the various values inside the clock chip, which is gonna include like the time and a little bit of NVRAM that's in there. And it received a 1, but it was expecting a 2, and it received a 2 and it got a 4, and so on and so forth. And you can like scroll through all this stuff here, and it got back nothing of what it expected. Obviously, there are some values in here that are going to be just garbage, and that's obviously because the configuration is lost because it's just garbage inside the chip. But a bunch of these things will have consistent values because they're status bits and stuff like that, and it's not getting anything back that it expects. Every single address gets back the wrong thing. Well, that pretty much tells us one thing. That tells us either the clock chip is bad, or the logic that connects the clock chip to the CPU is bad, because there's going to be some buffers and stuff like that, or potentially the select logic for the clock chip is bad as well, because just like any other peripheral, you need to turn it on and tell it, hey, I'm talking to you, respond back, please. So it's got to be one of those things that is the problem. Now, when it comes to the multibus error that we're seeing up here, this multibus failure, notice that it comes before the clock test. Well, I asked the folks on Discord to look at the flow of the diagnostic, and I wanted to know, does this ROM check the contents of the clock chip, of the NVRAM in the clock chip? That's the configuration data. Does it check it for multibus configuration? Like if you have a card in there that's a multibus card, does it go to the clock chip and say, hey, load the config, and maybe in there's some values for whether you have multibus cards? And that causes this multibus test to actually fail because it's reading back garbage that actually says that there's a multibus card, which of course there isn't because there's no cards in there, and that's going to fail. And the reason why I think this is exactly what's happening is if we go back and we look at what happened with this machine on one of the times I turned it on, it got a multibus error. But it didn't get the clock failure, but it got a multibus error, and then it said config value invalid, like the checksum thing was wrong with the config value. Well, on the next reboot, the multibus error went away. I think what happens is the system automatically, once it detects invalid configuration in the NVRAM, reconfigures it, probably sets it up to like a base value with like the baud rate, 1900 baud, and no multibus cards and whatever stuff like that. And then it should write that into the clock chip. So on all subsequent reboots, it shouldn't give you a multibus error, but except it did on that first one because of the corrupt data. Well, in this case, it can't do that. It detects that the config value is invalid, but it can't write back to the chip because something's wrong with that part of the circuit, right? We've already determined that. And therefore, every time we power this thing on, it's going to get a multibus error. So I have a feeling that if I fix the clock circuit, the multibus error will go away. It might happen one time, but on the subsequent reboots, it'll never come back. Of course, I have no battery in this machine, so powering it off might cause the multibus error to come back, and then you got to do one reboot cycle, and then it should go away again. Or I can install a battery so that once it sets up the config values, then it should go away. My presumption is inside the operating system, there's probably a command in there to configure the multibus cards, for instance. Like if you're adding like the 8-port serial card that's a multibus card to bring this up to 16 users, there's probably something to configure that. It writes into the NVRAM so that on subsequent boots, it's able to test that card, goes and checks what the contents of that NVRAM is. It says, oh, you have one of those serial boards. Cool, I'll do a little test on there. Good, passes, multibus good. Or there's a problem, multibus failure. So that's my logic and my reasoning for why we're getting 2 of these failures right now and why I think they'll both go away once I fix the clock calendar chip. Before I go back over there and start poking around the clock chip to see what activity we see on the pins, I'm just going to take a little bit of a tangent here. Remember I was trying to run some commands that I saw in the ROM code, and it looked like it was trying to load them off of tape, and it was of course not working because I don't have the tape. Well, what you see here on screen is that ROM code, and we have various things like format, MKFS, restore, file system check. When I typed all these commands, none of them actually worked. Well, over on Discord, a user, Transrail, found some old code here for an older version of one of these Plexus systems, but you can see here it has the Plexus boot ROM 1.0, and it seems that it's talking about using these commands. But the interesting thing is, these commands exist both on the hard drive and on the tape, and when you just type MKFS, it seems to try to load it off tape for default, but they're also on the hard drive, and I think they're on this hard drive too. So this stand directory, which I think stands for standalone, which means it doesn't require the rest of Unix to be running. I think we can run these from the boot ROM there in the colon prompt. So back on PuTTY here, the thing has failed. So again, we just push the exclamation point, and that drops us to this colon prompt. Well, I don't want to run the MKFS command, that's make file system, right? But Transrail actually found a list from, I think, some source code for an old version of Unix. All of the commands that we can see in the ROM. I mean, pretty much everything that's in the ROM is here, except for, I don't think dconfig is actually there, but the rest of this stuff is. And this looks like it's actually using these commands here to move these onto tape, right? See, it says tape colon, and it's using dd in file out file over to the tape. But some of these are gonna work. So one of them is stand/help. And I know I tried to run that in part 2 and it didn't work, but let's give that a try right here, stand/help. The hard drive is connected and spinning right now, by the way. And what's gonna happen? It's gonna hang. It's what's gonna happen. I see the hard drive LED blinking. Oh, that worked. That freaking worked. Look at this, display tape content. So yeah, this seems like this is a tape thing. These things are actually on the hard drive. They should be. Look at this. File 2, a copy of the Plexus System 5 Unix, the disk formatting config program, disk as in hard disk or floppy disk, I don't know, it doesn't really say. Construct a file system, restore the file system, check the consistency, file system check. You can use dd to make copies of stuff. There's the file dump program, which I guess will list the contents of a file. Interesting. So we have du for disk usage, ls, and cat. Type return for more information about this item. Okay, just a few more files here. File 20, the minimum file system required to boot Plexus System 5. And file 21, a complete release of Plexus System 5 in CPIO format. All right. Right, so this tape contains the programs needed to bring up software on a new system or restore the system. So this is coming from the hard drive, but what's cool about this is it's possible we could reconstruct a tape image. I don't have a tape to put in the drive, but maybe with the Blue SCSI we can emulate the tape drive and then we can recreate it and actually be able to start from scratch and have a larger hard drive partition, for instance. You know, if we use an emulated hard drive, I mean, there's all sorts of possibilities, right? Type 1 followed by carriage return to display the menu, or type 2 to display the tape contents. I think this is exactly what we've seen already. Oh, look at this. More information, this menu, display the tape contents, recreating system software, standalone programs. I mean, let's look at 5 here. I want to know if I could format a floppy disk. Formatting the disk, sparing tracks, initialize the disk is also used to configure your logical disk. Please consult your manual. Okay, I think this is for the hard drive. Let's look at number 8 though, disk format information for format. Oh look, different hard drives. What's kind of hilarious is it says 8-inch and 14-inch. The thing is, the hard drive that's in here is a 5 1/4 inch. So I have a feeling this stuff is like left over from the old versions. As far as I'm aware, the P25 and the P40, those like the big heavy duty Plexus systems that had a lot of cards in them and stuff like that, they used 8 and 14-inch hard drives. And it seems like when they ported that stuff over to this, they never fixed this. So yeah, clearly this is inaccurate information. So let's look at number 4 for standalone programs here. Certain standalone programs must be run before booting Unix. They perform a number of tasks necessary to allow Unix to run on a new system. Catastrophic system error results may require these programs to run. Okay, so like, you know, making new file systems or checking the file system, things like that. And definitely the way the disk partitions are set up on this thing, it doesn't really has a partition table, but the format is dev disk and then 0s1. So I think it's SCSI ID 0 and sliced 1, sliced 2, sliced 3, things like that. When we actually booted up the system in part 3, the user partition was being mounted and the root partition was being mounted. And I think it was like slice 1 and slice 2 or something like that. And the next page here talks about the logical partitions or volumes on the first default disk. And then we have something called ISBC disks. Are these Intel multibus drives? IS instead of DSK. And then PD is the IMSC drive, and then the Zylogic. I think people will probably know more about this than me, but I have a feeling this is probably all leftover stuff from the old systems as well. That definitely had a whole bunch of cards in them for accessing disks in different ways. But look at this. Dev RFP 0M is the floppy drive, and then RPT 0M is the tape, and then you can do it with no rewind. All right. Okay, so what we know for sure is that I can run these commands directly off the disk, but they need to be in that stand directory, and I just don't know if like ls and cat and stuff is. They would be on the tape if we had that, but I don't think we do. So how do we exit out of this? I think we do -1. Okay, so let's try stand ls. Let's see if it's gonna give us a directory listing. Okay, well that's a bit odd. We got $2 and oh, it works. It freaking works. So we're able to see the hard drive, like the main drive here. Right. So I guess what happens if we run this again is it's actually asking me to add any kind of command line parameters. So if we want to look inside of a directory, because I do want to look in the stand directory here. So there it is. Those are all the commands that we can run right from this boot menu. So without even booting to OS, these are all available for us. Cat, whatever ccal is. Oh, that might have something to do with the calendar. Let's try that. Stand. Oh no. The backspace key is misconfigured. It's not Control H, which it needs to be in here. Stand/ccal. I have a feeling this has to do with the clock calendar. That would make sense. I don't think it's going to tell us anything. I mean, the clock calendar is clearly not working, as the diagnostic test showed us. What the heck is this? System diagnostic configuration, Rev 1.0, diagnostic console. Oh, does this let us set a different serial port to be used as the diagnostic console? Baud rates? Oh, this is it. This is definitely how you configure the clock calendar, the defaults that are in there. It's like the CMOS setup for the system. Are we going to change the baud rates? No, we'll just leave those alone. And this is not going to work anyways. Memory size, 512K? No, it's 2.0. I don't know if we type 2.0 MB. Doesn't really matter, right? Because it's going to figure this out. Auto boot is set to no. Obviously, we have it set to yes. When you power up the machine, it's probably just going to do the /Unix and just boot right in automatically. Model P15. All right, maybe this is how you configure whether it's got the multibus or not. ICP. Okay, so ICP is the intelligent communication processor. That is what adds those extra serial ports. If the system thinks it's a P20 and it has the ICP installed, it's going to probably check those and result in the multibus error. This is all confirming exactly what I was thinking about. The clock calendar was causing the multibus error. All right, ACP is another communication processor. It's like asynchronous or something like that. I saw that in some document. Look at that, Ethernet. Does anyone have a multibus Ethernet card? Can we get this thing on the freaking internet? Oh, would that be cool or what? Clock speed? What? I'm pretty sure this thing runs at more than 10 megahertz. I think it runs at 12 and a half. Maybe this has something to do with the like timing loops or something like that. SCSI controller, 0 in system. I mean, yes, right? It has a SCSI controller. SCSI 0, LUN 0. Is it hard drive, tape, or floppy, or none? Well, I know that the Omti 5200 that's in there, the hard drive is configured as LUN 0, the floppy drive is configured as LUN 1. So this is definitely HD. I mean, I'm typing this stuff, it doesn't really matter. Obviously, this is a floppy, and then none. For this, I guess you just go through them. Is SCSI controller 1 in the system? It's funny how it calls it a controller, but I guess it's talking about the actual drive. Yes, it is. Is SCSI 1, LUN 0 a hard drive, tape, or floppy? Well, I happen to know that is the tape drive. And we can just do none on these. And there's nothing else. So we have another SCSI controller in here, 2, 4. Oh, it's asking us all the IDs. I mean, I guess we could have multiple controllers. I could put more hard drives in this thing. SCSI ID 7, isn't that the actual main motherboard? But we'll just say no to that. Is all data correct? Yes. Update configuration? Yes. I mean, it's not going to work. The clock chip is bad, but it's so cool. We can configure the system right here in the boot menu before booting the OS. I just didn't know how that would work, and now we do. So let's do stand ls. And actually, what I wonder if I can just do that. No. Okay, stand ls. All right, I hear the hard drive doing stuff. It's funny how long it takes just to do a simple ls, but I guess because the OS is not running, maybe the ROM code is very slow and inefficient. But I know now I can type stand here, and there we go, we can see the other commands. Okay, so cat is obvious, ccal is obviously the configuration, core, maybe a core dump, disk usage, file backup, format, file system check. We already know the file system is good. File system DB, I don't know what that means. Help, ls, make file system, OD, which I think was the dump, and then restore. Let's just try stand OD, and let's see if that does anything. I'm assuming it's going to ask for something to dump, and I could try dumping the kernel, which I think is just /Unix. Yep, /Unix. Okay, there it is. Look at that. It's dumping the contents. Right. All right, that was a very fun diversion. Let me use my old screwdriver here, and I'm going to shut the system down because it's quite noisy. And the reason why I did that is because I think we need to do a little poking around to see how the circuit is designed that actually connects to the clock chip. Now going back, I had mentioned that we were able to recover some data off the hard drive, and in that data was a net list and a parts list for this actual computer. Yeah, it's completely mind-boggling. Well, in the diagnostic process of trying to find the bad flip-flop that was causing the RAM not to work, I had to go through, and I have my papers over here, I did a whole bunch of like manual work, going back and forth and cross-referencing all these different files to figure out exactly what chips connect to what signals and how to like trace them through to figure out where the signals were going wrong. Well, it turns out the Discord channel has come through again, and there's now a utility to do it for me. I don't have to do it by hand anymore, and it's going to come in super handy because we're going to do the same work on this clock chip to try to figure out how it connects to everything. So what we have here is a Python script called netlist, and let's take a look at that real quick. And it I don't know, does a bunch of stuff. It's actually not very long of a program, but I'm not very good at Python. Whoops, I don't know how I was editing there, so we'll exit out of that. And what it's looking at is this cad.temp file. And I think this is like an amalgamation of the data that was recovered off the hard drive in a way that can be quickly parsed by this Python script. Well, I just took a look at the computer, and the clock chip is part number U2H. And all we have to do is run this command with the parameter of the chip that I'm trying to enumerate all the signals on. And we do that, and boom. All that work I was doing manually is now done in mere seconds, not even seconds, in a second. So that's the clock chip, MC1468818, 24-pin DIB. These are all the nets. Now, unfortunately, a lot of these nets, and that's just the way the files are, they're not really named anything. It's just net and then number as opposed to a name like ground or, M reset. But what this does, it shows each of the pins that is connected to something, and it shows which chip on which pin it goes to. Now for ground, for instance, it doesn't really show it, and that's because if you look at the net list under ground, it's like a zillion chips on there, so there's no point to look at that. So anytime there's a plus 5 volts or VCC or ground, it doesn't show it. Now this is a clock chip. It doesn't run on the normal 5-volt circuit, it runs on a BAT circuit, B-A-T-T. And that's because that's normally hooked up to the clock battery, because this chip needs to stay energized while the system is off. Also, due to a little quirk in the way this thing runs, anytime there's a pin that's not connected to anything, instead of saying NC for no connection, it doesn't list it. So the reason why there's no pin 1 is because that chip must be just not connected to anything on this machine. Now, a feature I had asked to be added to this, and Peter, who created this, is working on it, is to enumerate if the pins are not connected, just like print that so we don't, miss that. But also to use commonly available databases that are existing out there to tell us if the signal is input, output, or both. And also if it's a standard chip like a 74LS00 to tell us what actually each pin is. So there are databases out there that have that information readily available. And for this clock chip, for instance, well, we don't really know what any of this stuff is here, not without looking up the data sheet. So that one may never actually be look-upable, but on a lot of other components, they are commonly available in databases, and it's just a handy time saver to not have to go look that stuff up manually. Either way, when we take a look at this, a few things we can ascertain right away. So M reset, I happen to know this is the reset signal that goes into that chip from the reset circuit. And where the power supply stopped working for reset, that is where I connected the ATtiny reset signal in. I actually soldered onto the chip right on the clock chip on pin 18 because I knew that was the input for the reset circuit. And I happen to have cut the trace on the back of the motherboard that goes to the power supply because the power supply circuit doesn't work. So I just cut that trace. So that signal is reset active low. And then the bat signal, we already know that that's the battery. And this signal right here, cal.ce, calendar chip enable, I'm assuming. And whenever it has a little dash after it, it's the older convention, but that means that that is an active low signal. On a more modern design, you might write a /cal.ce or cal.ce with a line over it. All of those things mean the same thing. It just means that that signal is active when it's low. If that signal doesn't go low, that means that chip is never going to communicate on the bus. And that goes the same for ROMs or anything else you're trying to troubleshoot when there's an enable problem. Now, when we take a look at these other pins here, 4, 5, 6, 7, this seems a lot like data lines or something like that. So let's just take a look at one of these other chips here. So all we have to do is just run this again with this other chip. Oh, this is an LS244. So yeah, this must be a data line. And in fact, what was the net? I don't know. The net we were on was like 734 or 732 or whatever. And 734, yeah, okay, so see this? So it has BA, DMA. So DMA is the processor that's running the diagnostics. BA is buffered address. That's what I'm assuming that is. And I happen to know this chip uses multiplexed addressing and data lines. So that means that the 8 lines both handle addressing and data. So if we do this other chip here, oh, there's a lot of stuff on here. This is going to be data. Yep, BD, DMA. So buffered data. DMA 7, 6, 5, 4, 3, 2, 1, et cetera, et cetera. But there is data line 0, so we have 7 all the way, 6, 5, 4, 3, 2, 1, 0. Yep, okay. So we know for sure, going back without even checking the data sheet, that almost certainly these signals right here are going to be all the data and address lines. So we know for sure if one of these chips, this LS244 or the LS245, aren't being selected correctly, then the clock chip will never be able to talk on the data bus. I think let's not get ahead of ourselves. First thing you always need to check if you're trying to figure out why something's not communicating on the bus, a chip that is always a chip enable line. So let's take a look at pin 13. I'll get the oscilloscope hooked up. The scope probe goes to the Zoe ZT703S, whatever this thing is. A few people have asked me about this, like, oh, what am I doing using this thing? I bought one of these on a whim. This thing is cheap. It was like 70 bucks shipped. It's a decent oscilloscope. It's actually not bad. I don't love it, but I don't hate it either. And I like the form factor, and it's an okay multimeter. And after some firmware updates this thing has gotten, this is actually not a terrible device. Now, the reason why I did not review this is there are so many other reviews of this. And by the time I got it, like 50 other channels had already done it. And I thought, what's the point? But if people want to see me review this, then I can. But ultimately, it's a decent device. If you need a cheap $70 oscilloscope and multimeter, it's not bad. USB-C updates and charging, and the screen is big, it's quite visible, and the update rates are decent. The UI is frustrating at times, but not that bad. I like it. It's not as good an oscilloscope as the Handtech portable scope I have, but the UI is better on this, and the screen is better. And my eyes aren't that good anymore. Anyhow, it's hooked up to the chip here, and when I power this on, the chip select line on here needs to be at 0 volts or around there when the chip is being accessed, at the minimum. So let's turn this on. I have the little plastic tool I'm going to use. Okay, it went up to 5 volts, so that's okay. It's like it only needs to go low while the chip is being accessed. If it's not being accessed, it's fine, it's up at 5 volts. Now over on the screen over there, I can see the diagnostics running. It just says self-test 3.3, and we'll keep an eye on this right here and see if it goes low. And nope, over on the console, I can see that we have the self-test failure now for the multibus and the clock, and this never budged at all. Now, even though the update rate seems a little bit slow right now, I happen to know while this is triggered, it actually does update much more quickly. So if we had a pulse where it went low, we would have seen that. It would show up on this thing. That's one thing I don't like about it, is I don't like how the update rate is so slow on this when it's just sitting here not triggered. It's just in the run position. But anyways, it would have shown us something, and we got nothing. And that means, without a doubt, there is no way, let's turn this off because it is so noisy. There's no way that that clock chip can work if it's not selected. So I need to go back to the computer over there and let's figure out exactly what that thing is connected to and see what selects it, and then we'll fix it. All right, so back with the Python script, we're looking for this line here. It's going to two things, a resistor and a transistor. Let's start with R47 and let's see what that goes to. So R47 is on the Cal CE. Okay, that goes to the bat signal, battery. I happen to know, because I looked at this when I was putting on the little AT Tiny, the bat signal is just the 5-volt rail through a diode, because of course it needs to either charge the battery with 5 volts or it needs to power up the clock chip with 5 volts, or not 5 volts, whatever the original battery was, probably like 3.6 or something like that. So if we take a look here, designator bat not found. Did I type it wrong? I don't know, BATT. Well, okay. Well, anyways, it's right there and it's enumerating it. It goes to various things. So we know there's CR1, that's the diode that then goes to the 5-volt rail. In fact, I think if we do this with CR1, we'll see it's going to VCC. Yes, there it is, VCC and BAT. So that's, there's a little bit of a voltage drop through there. So the VCC becomes, you know, whatever, 0.6 volts less. But that does work, because when I was probing around to install the AT Tiny, I almost connected to this BAT signal, which would have kept the AT Tiny running all the time, which it wasn't necessary. And I decided to go not onto the clock chip, I actually took 5 volts off a chip that was right below it. I'll write down the signals we need to check. We need to just make sure that BAT does have that 4 point whatever volts on it, because the clock chip isn't going to work without it, but it looks like the chip select circuit obviously is connected to it as well, so we just need to make sure that that looks good. All right, the other component was Q2, so we have a transistor there. So let's take a look at that. All right, there it is. It's connected to ground. It's connected to the chip select line, and it's connected to 2 other resistors. So R51, let's see what that is. Okay, that seems to go to the reset signal. That goes to my AT Tiny. All right, and the reset signal goes off to various things. That is fine. And then what's R52? R52, that just simply goes to ground. So one of the things we can tell for sure here is that none of these nets connect to logic chips, none of them at all. Well, the only one that was connected to anything was this M reset. But we know that the chip needs to be enabled when the computer is not in reset. So I assume it's connected to that, something to do with it, like, I don't know, maybe it's a power saving thing or something like that. I'm going to think about this a little bit, but yeah, it's definitely not what I expected, because I would expect it to be coming from a logic chip. So anytime the CPU tried to talk to the click chip, it would be chip selected. Otherwise, you know, it would be idle. But I guess that's not the case. And actually, if we think about it for a second, remember that the data and address lines for the clock chip are connected through buffers, LS244s and 245s. That means that you could actually keep the clock chip selected all the time, and that wouldn't have any negative effect on the rest of the system, because obviously there's logic that activates this LS244 or the LS245 to connect the data or the address line to the clock chip. So maybe the clock chip is just enabled all the time, something like that. I don't know. Let me go have a think on this. All right, well, I was over on Discord chatting with Super SVGA, who helped me before, and Super SVGA came up with this simulation of the circuit, and we took the values of the resistors that I actually saw on the board, because they actually were different. Even though it said 10K, if we looked at the parts list here, wherever it was down here, yeah, 10K and 10K, I looked at the board and it actually had 520 ohm resistors here and here. It looked like what this circuit is doing, and Super SVGA kind of talked me through it a little bit. It looks like, as I thought, the clock chip is either selected all the time while the system is running, or it's not selected when the system is off. And this is probably some kind of a power saving strategy when the system is running on battery probably the clock chip shouldn't be selected. And if you look at this circuit, let's just talk through a little bit. So here's the 5-volt battery signal, right? And right now the transistor is not turned on. If this transistor turns on, what happens is this line through this resistor gets connected to ground and actually will pull the Cal CE or the chip select line down to 5 volts. Right now, you can see right down below, I can't point at it because if I move my mouse, or no, if I move my mouse, it goes off of it. The voltage of this signal is 5 volts. And that is when the reset line is not at 5 volts. So while the system is in reset, which means the reset line is down around 0 volts, or the system is just off altogether, which means the reset line is down around 0 volts, then the battery signal is just routed directly to the Cal CE line through a 520 ohm resistor. When the system comes out of reset, which means that the ATtiny pulls the reset line up to 5 volts, then you can see we have electrons flowing through here, and the Cal CE line now becomes 68 millivolts. So that is equivalent of a low signal, which enables the chip select line on the clock chip. Clearly, the circuit is not working properly. When I power on the computer, the system is actually in reset for a couple seconds. That's what the ATtiny does. So this Cal CE line should be at 5 volts initially for a couple seconds and then drop down to 0 volts. Well, it never drops, right? And when the ATtiny takes the system out of reset, 5 volts is available on R51 here, and that should bring this down around 5 volts, and that's just not happening. Now, when it comes to failed components, obviously if this resistor were missing, well, that's always going to be up there at 5 volts no matter what. And if this resistor was missing, now according to the simulation, even with that resistor open, it still works as desired. At 5 volts, the chip would be enabled, so it's not that resistor. And I don't think it's this resistor because they would be at 0 volts all the time. So the only possible candidates really are this resistor here, this 2K R51, or the transistor being bad, or the clock chip, I suppose. The clock chip signal could be bad internally, and it's forcing this transistor up to 5 volts. Although, if that were the case, that would be shorting through the transistor to ground, and the transistor would have got hot and died already. So I need to go over there and check a few things. I need to check that the base on the transistor is 650 millivolts or whatever it says there. I need to check that the emitter is actually connected to ground, because if it wasn't, if we take away this ground, then it's always going to be stuck at 5 volts. So I need to check that it's actually grounded. And I guess, I think that's it. I don't know what other things could cause this to go wrong. So yeah, I need to check that resistor. Well, I don't even need to check that resistor because this is a voltage divider right here. All I need to do is just check the voltage on the base to make sure that that's there, and just make sure that the emitter is actually connected. And I suppose I'll check to make sure the collector is also connected to here, because if this were somehow broken, like a trace was broken here, and this resistor just went right to Cal CE, and the transistor wasn't actually connected, then that would mean that it would also be held at 5 volts all the time. Okay, I know what to do. I'm going to go do that right now. All right, I am back, and well, I don't really see anything wrong actually. So the base is around 650 millivolts. That's what I saw on the multimeter. And then the collector was connected to the chip itself. I actually have full continuity between there. And the emitter is definitely connected to ground. So that really just leaves the transistor as the only bad part that could be bad here. Now this whole circuit seems to be something to do with power saving, as I said. And one easy way to test without even taking this out is I'm just going to ground the collector here, or just ground the Cal CE line altogether. That shouldn't cause a problem. It's not going to cause a short because this resistor is here, 520 ohms. It's going to waste a little bit of current, but it's no big deal. This is just a test. If this does work, then I'll just fix the circuit. I'll take the board out though and desolder it. So let's go do that right now. So what I've done is I clipped onto the chip select line and I hooked up a 100 ohm resistor, and that goes to ground. And this thing should be constantly enabled now. So with the oscilloscope hooked up, let's power on the machine. And yep, indeed, it's down at ground now. So this is working perfectly. All right, well, the system booted, and that's it. That's the boot we just had. And yet it's still telling us that we have a clock failure in the same error as well. So let's go in here and let's run that clock test. Now I think, by the way, I can run that test. Yeah, the H command lets me run it independently. Run clock A, TA, I think is what I type. No, we are still having issues. I've been poking around the clock chip. I don't see anything wrong. All the various signals, like there's a address strobe and a data strobe signal, those are good. Read write, looks good as well. In fact, when I run the diagnostics, the TA, where it lists all the memory addresses is getting wrong, I can see it pulsing. Everything looks like it's working. Now the question is, why do we not have a working clock calendar? My feeling is that I must have somehow damaged that clock chip when I was installing the AT Tiny. I guess. I don't know what else it could be. When I was using the Arduino to boot this thing, I hadn't yet soldered anything onto the clock chip, which is where the AT Tiny is. And I just don't remember if I actually got the system booted or not. I'm gonna have to go review my footage to see if I ever let the thing finish all its diagnostics and try to boot the system. Maybe I did, maybe I didn't. Well, to be honest, now that I think about it, I guess it's kind of irrelevant. The system's not working right now, even though it looks like it should. So I think what I need to do is I'm gonna socket the clock chip. And that will allow me to swap a different one in there. I'll just take the AT Tiny off. I have extras of those chips. I'll swap a different one in. I could even use a Dallas chip in this thing, and that should work. So I'm gonna go do that right now. Okay, we're ready for a test. This is the chip that was in there. I've removed it, and I have a bunch of chips here, spares, Dallas, but other 146818s that are compatible. So there's a Hitachi part in the socket there now. I have the AT Tiny removed right now, so I'm gonna have to manually bring the computer out of reset. All right, here we go, powering up. Computer's in reset, as it should be, and we'll bring it out of reset now. Here we go. Oh, one other thing, for that whole circuit with the transistor, I decided to remove one of the resistors, R51, which if we take a look at the list here, that says it was a 10K, oh, it was this one here, but it was actually like a 510 ohm resistor. So I removed that, and that actually renders the whole transistor circuit inoperative. So I just put a little jumper link on the back side of the board to bypass the transistor entirely. Look, look, the clock has not failed. So we're just getting a multi-bus failure, which is exactly what I would expect to happen. Let me grab the keyboard here. My hypothesis is if I reset the computer, we will not get that error anymore. But let's go into the DMA mode here and let's do TA. This is a clock test. Passed. Freaking passed. And T9 is the multi-bus test specifically. That's gonna pass. Right. Right, okay. So wait, this chip was bad? I mean, it was working. I mean, it was close to the battery, but it didn't look crusty. But I did solder onto the legs, so maybe I damaged it by doing that, I guess. I don't know. Okay, so to test my hypothesis about the multi-bus failure, I'm going to disconnect the resistor, which is gonna put the computer in reset, reconnect it, and we're gonna reboot. And if my hunch is correct, we're not gonna get the multi-bus failure anymore. So the computer's in reset, and now it's out of reset. Now, if we do get a multi-bus failure, it's not that big a deal because we know how to run the clock calendar setup utility now. And I'm just thinking here. So I think what I'm gonna do is I think I'm gonna install one of these Dallas chips. I just have to do the little Dremel trick to put a new battery on it because these are all dead. I have, how many do I have? I have 3 of them here, the kind that will work in this machine. Oh, we still got the multi-bus failure. Interesting. Okay, well, I have the hard drive stuff disconnected now. I'm gonna power the machine down, reconnect the hard drive and the SCSI, and let's see if I run that setup utility, if that fixes this problem. All right, drive is reconnected to power, SCSI is reconnected. Let's power the machine up, and I'm gonna clip the resistor on to bring it out of reset. There we go. I can hear the drive spinning up. All right, multi-bus failure. Yes, we know. Wow, clock chip died as well. I'm still a bit flabbergasted about that. Okay, diagnostic console, change the baud rates. I'm just gonna leave that as is. We have 2.0 megabytes. Auto boot, no. Let's put it to P20 since that's what this is, but we do not have the ICP or the ACP or Ethernet. Clock speed should be 12.5 as far as I'm aware. SCSI controller 0 is in the system, yes. It's a hard drive. Then we have a floppy. Then we have nothing. SCSI controller 1 is the tape drive, so that's TP. I mean, it doesn't really matter, does it? These other LUNs aren't used, and these other SCSI controllers are not used. Where's 3? It's funny how it skips over 3. All data correct? I'm gonna say yes. Let's update the clock calendar. Okay, let me reboot it again by taking the resistor off. All right, system is booting back up. If all goes well, we won't get that multi-bus error anymore. I'm keeping my fingers crossed that that's the case. It's just corrupt data. Oh, incidentally, when I was poking around on the bad clock chip and I had the oscilloscope connected, without a doubt, I could see the clock chip being accessed early on in the boot process. When you first power on the machine, this chip is read a bunch of times, and that's even before it gets to the clock test. So that means it is reading configuration stuff. Oh, clock failed again. No, no, no. Is that error different? A007. Oh, you gotta be kidding me. What's happening here? Okay, before I jump to conclusions, I'm not gonna worry because the way I was doing the reset with the clip leads, it's not ideal. I think ultimately glitching the reset line is probably not a good idea, you know, using the clip lead. That's gonna cause all sorts of weird issues. And okay, yeah, we lost the config info. Okay, whatever, let's boot the system completely. So I hit exclamation point and I'm just gonna push enter and hopefully the system boots. Hard drive light is blinky blinky. And let's see if it boots. Before it was freezing, right? After it would show the free memory, I think because the clock chip wasn't working. So fingers crossed, this actually works. Oh yeah, that was it. It's working now. So the bad clock chip keeps the system from booting. Oh, look at that. So it remembers the last time the system booted, and that's the time I typed in. And remember the first time we booted the system, it was 1989. So that confirms that was the last time this system was working. Is the date correct? I'm just gonna say yes, just to skip over this. Do you wanna check the file system? I think we're gonna say yes because the system did crash, and I'll let this run through the check. It was crashing in part 3 when it was getting those errors, right? I feel a big sense of relief here though that, yeah, the clock chip went bad and that caused this thing not to work. So I think what I'm gonna do is take this Dallas chip here. I'm gonna put the 2032 mod on it, use a Dremel to kind of eat away at the case a little bit. And then I will stick this in there and this should work in place of that. And then we should have a clock calendar that actually is able to save the settings. But the system is booting up here, which is excellent. There we go, we're ready for login root. And there happens to be no root password on here. We did learn that. And there we go, we're freaking logged in. Now I'm curious if there's a reboot command. So I should be able to run that ccal command right here as well. Yeah, oh, core dumped. Okay, you cannot run that command while you're in the operating system. I guess these stand commands do not work while the OS is running. They do not. And what I'm gonna do now is modify the Dallas chip and I will reinstall the ATtiny so we have a proper working reset circuit. And hopefully after that, the system is fully operational. Okay, the motherboard has been modified. I actually put the ATtiny on the back side and I have my Dallas chip all modified here with a CR2032. The one thing I forgot to mention is the original Motorola chip that I took off the board actually has an auto detection between Intel and Motorola mode, but all the later versions of that chip don't have that. So for the Dallas chip to work, you actually have to put a 10K or a 4.7K between VCC and the Sense pin, which is pin 1. It's a Motorola/Intel mode change pin. So to use this Dallas chip though, I do need to hook that pin up to something, and I hooked it up with a resistor on the back side of the board as well. This is exactly the same thing I had to do on my BBC Master 128 when I installed the replacement clock chip, because I think it also used the same exact Motorola chip in there originally, and I put the Necroware replacement chip in there instead of one of these Dallas chips. And that one also required pin 1 be pulled up to 5 volts, otherwise it wouldn't work quite right. So I'm gonna stick the Dallas chip in here with the battery, and let's see what happens. And I'm ready to steal this thing, turn it on with a screwdriver. Here we go. And I won't need to do the reset thing anymore. Should come out of reset. There it is, it came out of reset on its own. Now incidentally, when I had the Hitachi chip in there, that was the replacement chip that I put in instead of the Motorola chip. I think it also needed that resistor on the backside. Probably explains why it wasn't quite working with the multibus. We were still getting that error. I think it was because of that. Although, I guess we're gonna find out shortly if that was actually the case. Tape drive making all sorts of noise. Okay, multibus failed. As long as we don't get to clock failure. No clock failure, that's good. All right, config invalid, totally understandable. So what we're gonna do is we're gonna run that stand cc config program, not cc config, ccal. This will run off the SCSI drive. All right, diagnostic console, baud rates, nope. Memory size 2.0 megabyte, auto boot, nope. I'm just gonna leave this as P15 for now, just so it doesn't even do a multibus test anymore. Definitely SCSI controller, hard drive, floppy, and the rest is nothing. And I'm actually going to say no for the tape drive because I actually don't know if the tape drive is ID 1 or not. So we'll just skip past all this stuff here. All data correct? Yes. Update configuration? Yes. I'm going to do the old reset here with the screwdriver. And let's see what happens. Okay, there we go. System is rebooting. So theoretically, we should not get the multi-bus error, hopefully. And before, when I didn't have the resistor installed, when we did this, I got that proc error and a clock error. And I think that was because the resistor was missing. Let's see what happens. I kind of remember on the BBC Master, when I didn't have the resistor in place, there was a bunch of garbage that came back from the clock chip when you didn't have the resistor in place. So let's see what happens. I think we're golden, everyone. I think we're freaking golden. Because it's doing a parity check right now. Oh no, proc failed. Interesting. Procs mean, I wonder. So we didn't get the clock failure. We didn't get the multi-bus failure. Well, we can run that utility again. Stand ccal. Oops, that's not it. Stand ccal. But look, it definitely retained settings. 2 megabytes. Auto boot, no. So let's do P20. You know what? Before I press enter here, I'm going to hook the oscilloscope up to the clock pin on the 6810. I've never done that. So let's see what it actually is running at. All right, yeah, it's running at exactly 10 megahertz. At least, well, at least the processor I probed there. So we'll just leave that as 10 megahertz. And we'll just go through these. I'll just hit enter since it seemed to have retained everything. All data correct? Yes. Update information? Yes, we will. I'll reset the computer again. There we go. So interesting is the multi-bus error, it went away, but then we got the procs error. What does that mean? What is procs? So while we wait, it's kind of cool that the Dallas chip seems to be working. Definitely saved the settings, and the battery on there should keep it going for, you know, years and years and years. It's a very efficient chip. The Motorola needed that giant NiCad battery to retain the settings for any reasonable length of time, but the one that the Dallas has, there's that proc error again. I guess I should power the machine off and back on and see if that goes away. I'll just let the machine cool down for a moment. I guess this is the real test as well. Is the battery working? I used a little mini Dremel here to cut away at the side of it, and then my little engraver tool to cut through the pin. I like to personally cut the battery off that's internal, that's epoxied in there. I like to cut the little metal part that goes from the chip to that battery. That way, the battery I put on there, the CR2032, is not trying to like back charge the little whatever coin cell that's inside of there. Okay, come on. No procs error. No freaking procs error. Nah, proc fail. Let's go in here and let's run the tests again. I think I just hit T. This will run the entire gamut of diagnostics here. The funny thing about that proc error is when the system booted up before, like when the clock was corrupted, we didn't get it, and now we are. So it feels like it's something to do with the config settings that I set up there, because the error appeared after I set up the clock calendar with that utility. Okay, wait, look at this. Procs. SC7 not expected, failed. SC7? Ah, is that SCSI? SCSI controller 7, and I hit no. Let's fix that. I'm gonna reboot the system, and I'm gonna put yes on 7 and see if that does anything. All right, hit yes. And it's asking what it is. I don't know what it is. I don't know, I'm just gonna put HD. I don't know what else to put there. And we'll say yes, update config, sure. And I've escaped right to the DMA menu here. And I think if we do H, we can just run that particular test. TF, no, same thing. Oh, different error code though, look at that. F022, and before we were getting F035. Now I notice if I hit Q, aha, look at this. System configuration, SC0, SC7. Is the tape drive SC7? I mean, the tape drive is a separate SCSI device. It's not part of the interposer, which is definitely ID0. So SC7, it's gotta be the tape drive. Okay, I'm gonna put yes, and we're gonna do tape, TP. And there's nothing else on that one. Is this correct? Yes, it is. Update config, yes. Reboot the machine over there. And let's see if this does the trick. It's quite the learning experience. It was interesting to learn that in the DMA menu, Q gives us the system configuration. And normally when the diagnostics pass, we will see this exact message. I think it just kind of tells you like what it's found. And let's see if that does the trick. You know what the fact is, how it skipped SCSI ID 3? I think that kind of tells us that the computer itself is SCSI ID 3. That's unusual. I don't think I've run across that in my entire career. Oh yes, that was it. That was freaking it. This thing is working now. Hit enter and we're gonna boot into Unix. Quite the learning experience, but you know what? The clock is good. I can turn this off and tomorrow it will freaking remember all its settings because that battery is on there. That is awesome. We ended up in single user mode. So I think we could do that. And this should put us, yeah, it should continue. Oh, look at the time. Oh, it's because it's corrupted and it's reading it back from the actual clock. Question is it gonna stay working? Or is it gonna fail in some other spectacular way? I don't know. All right, there we are. It's logged in. It freaking is working again. Oh, that is just so great. What I should do is try to do a shutdown here. Shutdown program. System being shut down right now. So that was a broadcast to all other users on the system. I'm gonna turn this off tonight. I'm gonna go to bed. And then we will see in the morning if this thing boots up properly without any errors. I really hope this thing works. I'll see you in the morning. It's been a couple days since I took out the bad clock chip. The Dallas has been in there with the battery the whole time, and I think it's now time to test this thing. Did the Dallas clock chip retain all my settings? And will we actually get a boot with absolutely zero errors? Guess we're gonna have to find out. And the Plexus is all back together. The one thing I ran into is that Dallas clock chip sticks out a little far, and it actually caught the lip of the case as I was sliding it on and it knocked it out of the socket. It actually clears the side of the case without an issue, and it even clears the lip. You just have to make sure when you slide this on, you don't sort of tilt it one direction, which just makes it a little too close. I'll have to put a note on the back that says when removing case, be cautious of the battery on this side, just to remind myself not to knock that out next time. All right, let's power up the beast. Here we go. All right, we don't see the Plexus banner because I had to restart PuTTY when I first turned this on. I always forget that when my lab machine goes to sleep, for whatever reason, PuTTY loses connection with the COM port. Hopefully it is actually working. And one thing you can tell is, oh wait, look, yes, it's freaking working. All right, so auto boot is turned off. All I have to do here is hit enter. By the way, system 5.2R8, what does that mean? I don't know. There we go, yep, run level 2 automatically. Is the time correct? June 4th? Yeah, that's it, 1:31. That is literally what time it is right now. Ignore the year being wrong. That's a problem with the clock set utility. Time is correct. Let's check the file systems again. I mean, we don't really need to, but may as well. This thing is actually freaking working. Wow. There we go, I just broadcast it freaking works to all the other users on the machine, which is no one right now. This thing is actually fixed. At least it's fixed for now. Part of me can't really believe that this computer is actually working. So I think what I'm gonna do now is just let this thing sit here, boot it up into Unix for a while, and make sure that it doesn't fail. I want it to at least run for, let's just say 3 hours. I'm just gonna pick that amount of time arbitrarily, and hopefully it stays working, and then we can consider this thing fixed. At least fixed for now. And it's been a few hours since I powered this up, and the Plexus P20 has been working perfectly. Well, not quite perfectly. I think I figured out there's something going on with the floppy drive on here. I don't think the spindle is spinning, and anytime you try to access the floppy drive, what happens is the interposer gets confused, and the floppy LED stays on, and then the hard drive is no longer accessible. So it actually crashes the system. Well, it doesn't crash, it just halts the whole system. Because even if you try to go to a second serial port and log into another console, it can't do it because the hard drive is inaccessible. It's probably one of the negatives of using the interposer that handles the floppy drive and the hard drive at the same time. I think what's going on is because the drive's not spinning, there's no index pulse going to the interposer. That must confuse it. So when it comes to future plans for this machine, now that it's working, there's still lots I want to do. First off, we have to finish sanitizing the hard drive image that we've created of this thing. That way I can upload that to GitHub so people can take a look at it. I've had a lot of requests for getting access to the hard drive image. So hopefully by the time this video is out, I will have already been able to do that, and it will be uploaded, and I'll link below in the description to that image. I also obviously need to fix the floppy drive because that's not working. So take that out, see if I can get that working. I'll do it externally on a PC. Also, I want to get the Blue SCSI working with this machine. I talked to Eric, who's one of the lead maintainers for the Blue SCSI project, and he gave me some tips and pointers on configuration options to use because this thing obviously is expecting the Omti 5200 in there for the hard drive to work. So in a future video, I'm going to try that out because I need to let Eric know if there's any fixes that need to be made to the source for the Blue SCSI to add this weird, rare computer to the compatibility list. I'd also like to try to figure out how to get files on and off this computer. The floppy drive, obviously, if that were working, would be one possible way, or potentially copying Kermit source code or Z-modem source code and then transferring files over the serial port. But right now this seems to have a UUCP mechanism for transferring mail between various systems over the serial ports. But I think I'd like to get something a little bit more direct, like the floppy drive or some other way to get stuff on and off of this. If the Blue SCSI works, I can obviously take the SD card out and put that in a modern computer, and then hopefully we can figure out how to mount those images on something modern to copy files on and off this as well. Anyhow, as you can see, there's still lots more to do with this machine. I might need to take a little bit of a break though and work on some other stuff for a while. It's been sucking up all my time, this beast, but I do like it, and I'm really excited that the thing is working, and I'm definitely going to do some more stress testing of this thing and let it run for even longer than just a few hours, just to make sure that nothing else is ready to break on this thing. But so far so good, 100% stable. And the last thing I want to add is I do apologize. This video I know is a little bit all over the place, especially while I was working on the clock circuit. I edited some of the video already before I've done this outro, and I noticed, I don't know, it's not up to my usual standards. So hopefully you liked it. If you did, thumbs up. If you didn't, you know what to do. A huge thanks again to everyone over on Discord who has been helping me with this thing. I really don't think I would have been able to get this working, or it would have taken me way longer if it wasn't for the help that everyone over there has been giving me. And also a huge thanks to the folks who were helping me with the disk image and recovering the data off this thing, because obviously that hidden data that was on that lost partition was the other part of this machine that was absolutely essential for getting it working. So that's going to be it. Huge thanks to my patrons. Names are going up the side of the screen. They get early access to videos. They make it possible to do this full time. So yeah, big thanks to them. Thumbs up, subscribe, usual YouTube junk. And that's going to be that. So stay healthy, stay safe, and I'll see you next time. Bye-bye.